Hi, good evening all. This is Satyanarayana from that course instructor team of IT Madras. So today I'm handling the session. Maybe Atul sir might take some other session, maybe on Friday live coding one, or it might be some other session. So I think the PS Kiran is asking that, myself is Satyanarayana, maybe one of the course instructor. Yeah, this is my full name. Maybe sometime you want to tag anything, you can tag it. Oh, okay. Uh, So let's jump into the content. But before jump into the content, again, I'm giving you a gentle reminder. Maybe this could be uh, the final term where we want to record or live stream the things, because mostly whatever we have done so far is a quality kind of recordings are there. That best recorded sessions are already streamed. Maybe you can refer it, but live sessions are there if and only on the demand basis. That will be implemented strictly from the next term. This is another gentle reminder for all of you. Recording and live streaming will be stopped, but live classes are there. Course instructor classes are there on the demand. Like you will propose that one kind of concept, one kind of clarification. We'll come to the lecture and we'll teach you that the concept behind it or problem behind it. So how to solve the approach also we'll teach you. But if that is a new content, definitely we'll try to record a live stream. So hope you understand what I'm telling you, because actually we try to implement from this term onwards, but we are unable to do it. But next term onwards, it is done. Yeah, this is week number 4. Whatever you have done so far, from week 1 to week 3, it is different. Hope my screen is visible, because I'm sharing my screen. Is my screen
Yes,
visible?
sir, it's visible.
Yes, sir.
Okay. So I'm trying to use my basic rough work. So generally, whatever you learned in the PDSA course so far from uh, week 1 to 3, all this is maybe you learned linked lists, you learned stacks, you might learn the queues. All these are linear data structures. Linear data structure. So linear means it is simple. It is a sequential processing of data. Sequential processing. The name itself, it is there. Sequential processing of data. Like, even you take a linked list, we are always doing, we do that one direction of links are there. We try to traverse all the elements. But when it comes to the week 4 onwards to all other weeks, maybe week 5, week 6, I think up to week 7, I don't remember, but it is sure. So week 4, 5, 6, pretty sure. Maybe extra, I don't know. These are non-linear data structures. Non-linear. We try to work with some data structures. Those are non-linear. They are not sequential. The processing of elements is somewhat complex when you comparatively whatever you learned that week 1 to 3. But 4 to 5 and 6 and all these are non-linear data structures. These are not sequential. Hope you got it. What I'm trying to say that.
Sir, weeks is about heaps, no?
Heaps
Is
also, it is a non-linear data structure,
oh, okay.
because this is containing most random data structures like graphs, trees are there. These are non-linear data structures. They are not sequentially processed. Some standard algorithms are there. Based on the algorithms we are processing, so that we can say that these particular weeks are some complex concepts. So you must be very careful about understanding the concepts, so that you can easily get the good grades and good kind of application level understanding. These things you can understand from the week 4 onwards, if and only you focus on it, because additional uh, your contribution is required from week 4, not so that easy like week 1 to 3. Somewhat you need to focus more on from week 4. That is what from the week 4. So let me jump that complete walkthrough of the week 4. Shall I move for the week 4? Like complete walkthrough, maybe all concepts of week 4. Is it okay? Any specific
Uh,
concepts you want to ask him?
Sir, just a clarification. In the
Hmm.
lecture, sir has explained the implementation of DFS using recursion. So,
Hmm.
he said implicitly recursion works like a stack, so we don't
Hmm.
need to maintain a stack.
Correct.
So, is it necessary to use a stack?
No, no, it's not required that explicit stack is required. If you are using recursion, that is more enough because it's a backtracking. It is automatically done, so that we don't need stack
Yeah,
again.
yeah.
Okay,
So,
yeah, that's the easy implementation.
okay.
Okay, you not use another implementation of stack, but both approaches are there. Easy approach is that using recursive algorithm. Okay, yeah. Shall I jump to the week 4 concepts?
Yes.
Okay, okay. So the first concept of the week 4 is we are going with the graphs. So let's jump to the content of the week 4. First, we are starting with the week 4. Basically, it's a non-linear data structures introduction is started. So in that, the most interesting one and important one is that graphs. So the graph is simple. Maybe graph G, it contains that V number of vertices, E number of edges. Vertices, another name we can say that it is a nodes. Someone says it's a vertices, someone says it's a nodes. And E number of edges are there. So V is nothing but vertices. And E is edges. Graph is definitely combination of these two. So for example, so let me go with the example. Maybe you can say that as per your uh, GitHub notes only we are walking through. So hope my GitHub notes also visible. There is a simple graph was given. You can look at this one, this graph. So this graph, it contains that set of vertices and set of edges. Maybe I may not go with same kind of graph, or it might be something similar to it. A, B, maybe center they have taken C and E, and it's a D. So if you connect these through edges, maybe some edges, this entire one is called as a graph. So when you say that G is containing that V number of vertices, E number of edges. So what the V contains is all the vertices. If you could say that what are the edges are available as A, B, C, D, E. Totally 5 vertices are available. And edges you can compare it. Maybe someone says edges you can exclusively they can put it even E2, E3, but I don't want to do it such a way that even E2, E3. So edges it contains now. We have A to B or B to A, one edge is there. Of course, it is undirectional one. We will discuss undirectional or directed graph. That's a different issue. But right now, A to B, there is a edge. So A to B, there is edge. Similarly, B to A also one edge. We can say that because it's a vice versa. It's an undirectional one. So A to C, we have edge. And B to C, we have edge. And C to D, we have edge. And C to E also, we have edge. So totally 5 edges are available and 5 vertices are available. So hope you got this. What is the graph is? So graph is a simple representation of connecting that collection of vertices with simple paths, or we can say that edges. That is called graph. So hope you got it. What is graph is? Now this graph, anytime if you have any clarification, you can raise your hand. Immediately I'll interrupt my session. I'll get back to your clarification. Again, I'll send back to my discussion. So now this is a graph. The graph we are representing as a simple kind of vertices and edges. But how can we convert this one into data? Or we can say that data structure. We need to convert into a data structure. What you can say the data structure is? A digital format where it is some computer understandable format we want to convert it. So what are the different ways of converting that graph into the digital data or data structure format is? There are two ways of converting. The first one is that adjacency matrix, and the next one is that adjacency list. So adjacency matrix is simple. This is n cross n matrix, where n is the number of vertices, n is the number of vertices. So it contains that values of this matrices. This matrix, it contains a value of 0 or 1. So 0 means that there is no path or edges existed. 1 means that there is edges exist. So we can say that false and true. So basically, you know, everybody, 0 means there is no edge. No edge means it's a false. So 1 means there is edge, so that there is a path exists between two vertices. That is called n cross n matrix. What you can call is adjacency matrix. If you can say that adjacency list, it contains that a dictionary, what you can say that, so because basically, you know, the dictionary is in Python, a dictionary of each particular vertex, as a key, and adjacent vertices as list. I'll show you, don't worry about it. But both are different kind of representation. Any representation we can use it, but based on that data structure representation, the complexities are different. Same algorithm, it works on adjacency matrix, same algorithm, it works on adjacency list, but in the complexity concern, adjacency list is a better than adjacency matrix. So anyway, we will discuss using that GitHub summary. I'm going back to the GitHub summary because GitHub summary is having most of the code where I need not write any code here. So hope you understand up to this. Is it right? Up to this, you understand?
Yes,
Do you
sir.
understand? Okay, good. So now the basic terminology is there. Whenever, actually, before going for the actual coding part, we try to understand the terminology. So we know that what is vertex. Vertex is basically a node or vertex, we can say that. Edge is connecting two vertices. There is a path is existed between. And here degree is there. Hopefully, you know, degree means two particular in degree, out degree is there. But if it is unidirectional graph, the degree is just a total. For example, let me take this. A, B, and C. So what I do is I'm connecting this one. So what is the degree of this A is 2, because there are two edges are connected to the A. So degree is nothing but simply it is a undirected graph, means it is a degree. For example, there is in-out degrees are there. For example, I take that another graph. This we can take that. So what I do is a directional graph. So I say that it's a directional graph. I say it's a directional graph. For example, if you say that the in degree for this one is 2, but the out degree for this particular B vertex is 0. Is it right? Is
Yes,
it right?
sir.
So that if it is a directional graph is there, we have in degree and out degree. But if it is undirectional graph is there, it's a degree. So we don't say that in and out, because there is no in and out. So it is simply connected. So that is called degree or in degree or out degree. Now we say that path, a sequence of vertices connected through a path or edge. And remember, there is no repeating vertex. That's make sure. For example, if you could say that A, B, C, so you can have a path like this. So A to B is there, B to C is there, all the particular vertices are connected. There is a path is existed between A to C also, but indirectly it's there. A to B direct path is there, but A to C also there is a path is there, but it is indirect path. C to D might be there. This is also path existing. But we don't say that again D to A, we don't call it a path because already A to D is connected via B and C. It's enough. Again, we don't say that the path is repeated, that D to A. That called cycle. That's a different issue. That's what the next term is telling. The cycle is a path that starts and ends with the same vertex. For example, if you start it from here, you end it from to here, that is called cycle. But path means it's a starting vertex to last vertex. That's called path. Cycle means where do you start it? There you are ending is called cycle. So you should remember these terms. So this is another term of graph.
Sir,
Next, tell me.
then the start and is repeating. So if the vertex is repeated, then technically it's a walk.
That's called cycle. That's
No,
called cycle.
no, I'm saying it's written cycle is a path. No, but the start is
No, no,
repeating
no,
that
no, no.
then it should be a walk.
Path means beginning vertex to last vertex we are reaching. Clear? Is the last vertex is a unique vertex or same vertex it is started?
Yeah. So if the start and destination is both the same,
Then it is called cycle.
then it is cycle.
Then it is called
Then
cycle.
for a for a path, the repetition is not allowed. No, repetition of vertex.
That's what both are different. I'm telling, both are different. I'm telling that both are different. This is different, where it is no repeating of the same vertex. Okay, all vertices are independent and they are connected with no repeating, like A to B, B to C, C to D. Is it right? Is it a path or cycle?
From A to D.
It is a path.
A to D is a complete path via B and C.
Yeah.
You are reaching to the D or not?
Yeah.
There is a reachability is there.
Um,
For example, this is there. Is it called path or cycle? You started from C, you ended to the D, it's over. Again, you are trying to D to C means where you started, there you are ending. That it means what? It's a cycle. So this is a cycle. Cycle is different. If the same vertex is repeated in the path, that's called cycle. Clear? Hello?
yes, that's fine. But path is about reachability. No, path defines the reachability from one vertex
Reachability.
to another
A
vertex.
to A to D is reachable.
Yeah. So
C to D is reachable.
yeah, but
So
in
D
a
to C
path,
also reachable. But
yeah.
where you started, again you are coming back using edge, a new edge. I mean that same edge is not a new edge. Then that is called cycle. Is it right?
Yeah. So in a path, we
Mm.
cannot repeat a vertex, right?
Correct, correct.
So if the repetition of the vertex is allowed, then it should be technically a walk.
That's called cycle.
No, I'm not talking about cycle.
If
Just talking about the.
repeating of same vertex, can you tell me any graph repeating of same vertex where it is started? That is
Um,
definitely cycle. Can you tell me that anything repeating of same vertex? That is definitely cycle. Even for example, if you write a self cycle, also it's a cycle. Is it right? If repeating is there, what it is called?
then it is.
Cycle. Over. Clear? Hello.
No, sir, but there
No,
is
tell
some
me some
difference.
graph. Tell me some graph. Tell me some graph. Whatever you want. Tell me.
A B C D E
Okay, A, B,
and
C, D. Yes, yes. A, B, C,
C
B, D.
D.
Okay, it's enough, no? or E also required?
and E and F.
E and F also. Okay, E and F. Okay.
Mm,
Then tell me the path.
no, yeah, from C to F there is an edge.
C to F, there is an edge. Okay.
D to F, okay. So
Okay.
and A B,
No, no, tell me. C, D
A
to
to
F, you
B,
said. Next edge, tell me.
A to B,
A to B, okay.
and B to C,
B to C, okay.
and C to E.
C to E, okay. C to E.
Mm, 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 C to D.
C to D, okay. Is it cycle? Nope, no cycle. No, no cycle.
No, 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 there is no cycle.
Then it is called path. Then how can you make it cycle? Any
So
cycle is there? Any edge is repeating the same vertex? No. Is it right? How can you make it cycle?
no, I cannot make a cycle.
You if you make it this one, is it cycle or not? Is it right? Hello.
Yeah, yeah, yeah.
So that if repeating of vertex in the path is there, that is called cycle. No, is it clear?
Um,
Over.
yeah, but cycle is like a looping. It starts and
Yeah, looping,
ends at
looping.
the
Cycle
same.
means loop only. Yeah, cycle means loop. See, you
Yeah,
started from C, E, F, D, and again C. You are repeating, no?
yeah. Then the source and destination is the same thing.
That's what they are clearly said.
Yeah,
If it is vertex is see, the simple path is a path where there is no vertex is repeated. Here it is repeated. Both are contrast things. Is it right?
yeah, in a cycle, only one vertex is repeated. That's the just the source. Which is the same as the destination, but
No, 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 no. Not one
in a
vertex. Any vertex.
walk. Hmm,
Not no, not any vertex. Start vertex, end vertex, or anything. Maybe you can start the traversing from here. Is it right? Is there any rule that I must start from A? I can start from traversing from E. Is it right?
hmm,
I can start from the traversing from F. Is it right?
yeah.
Hmm. So that these two are opposite things. Am I right or wrong?
Yeah.
Still, why you are worrying about this simple concept this much time? I don't think. Anybody, please. Maybe I'm something
Yeah,
went wrong.
but sir, in a cycle, I'm looping back to the same edge.
Hmm.
But in a walk, I'm concerned about reachability. There is no
Ah,
concern about. It's
no,
not
no.
about looping.
It's not about loop. That's what now this statement. What it is giving? Is it giving the same meaning of cycle or not? If it is repeated, no vertex is repeated. For example, vertex is repeated. What does it mean? Cycle or not?
Mm,
Why you are thinking about this many things? If vertex is repeated in the path, what does it mean? Is it cycle or not?
yeah.
It's a cycle over. Simple. Both are contrast things. No cycle, it's a path. Cycle is existed, it's a cycle. That's it over. Yeah. So maybe anybody, I might have went wrong. You can just because it's a simple concept. It's pretty straightforward. I don't think it is. Thing is, yeah. Shall I go for next? Yeah, please raise up your hand. Maybe who is speaking, I must know. Maybe that could be good for suddenly you're speaking. Okay, just raise up your hand so that I can come by name. Okay, shall I go for next?
Sir, can you move up a bit?
Hmm.
Can you draw that again? Or, yes.
You said this one,
Yeah, B to C, C to
then you
D,
said this one. Is it
C
right?
to E. Yeah, C to E,
C2?
C to E.
C to A.
C to E, E,
C to E. Okay, okay.
E for elephant, and
I
D to
think
F.
I think this D is not there. This is not there. No, this is not there. Earlier you did not use this one, right? Hmm. Then, sorry, I'm sorry.
Uh, yeah,
Up to here is okay. Then C to E you said, right?
yeah, and D
Okay.
to E, C
D
to
to
D.
E, D to E is there? No, no. D to E did
Mm,
not. D to E is there? C to
mm,
D you said. D to
yeah,
F you said, right?
yeah, C to D.
D to F you said, right?
Yeah,
Now, what is this? It's a path or cycle?
yeah, and also better D to E.
Wait, wait. First it is path or cycle.
It's just path. There is no cycle.
Okay. Then what is the edge you want to connect?
I want to connect D to E.
D to E. Now what happens? Is it cycle is happened or not?
Yeah, now there is a cycle. So,
Because of D
yeah,
started E and then C again D you can come back. No, another new edge.
yeah, D, C to D, C D E is a cycle. No,
No, CD is
supposing,
not a cycle. CD is not a cycle. C to D, D to E, again E to C, new edge is there. Is it right? This is a new edge.
yeah,
This
C,
is this is ah.
yeah,
Via new edge, you are connecting back to the previous one.
yeah.
That is called
So,
cycle over. Ah.
yeah, cycle ends here. Supposing if I want to check the reachability from C to
No, no, no.
A,
Let's see. Forget about
the,
reachability. Reachability is different. Reachability means you are connecting from source to all other vertices, right?
yeah,
Now,
so,
fundamentally, what is the difference between path and cycle? Did you understand or not?
yeah.
Cycle is there means that means that no reachability. Reachability is there. Whether cycle means you understood?
Yeah, cycle is fine. So if I start from
Ah,
C and
ah,
come back
ah.
to C,
Cycle is there means
extend the
reachability is not there or what? It's there, no.
yeah, reachable. Mm,
Reachability is there. C to E you can reach it. C to A you can reach it. C to F you can reach it. You can start from anywhere. You can reach to everywhere. That is called reachability, right?
yeah, so that is okay. No,
Hmm.
so when I talk about path, if I want
Hmm.
to
Hmm.
talk about the reachability from C to A, then
Hmm.
I can go from C to B and B to A. So
Over.
that is a path. There is
That's a
no
path.
repetition of vertices, and there is
Clear.
another way I can go through it, so with some long distance, like
Hmm.
C to D and
No,
D
no.
to
In the
E.
in the in the graph,
Yeah,
in the
yeah,
graph. So forget about in the graph. This
mhm,
graph, G. This graph is called G. Clear. This entire
yeah,
graph is G. Is it
yeah. This is G.
acyclic graph or cyclic graph? Tell me.
There is cycle.
Then over. Why to discuss this one?
Uh,
Why you are
so
discussing this much? Path is a different thing. Path is connecting from one vertex to another, either directly or indirectly. Over. Again, you are discussing reachable. Reachability has again different meanings. Clear? Whether you are
uh,
reaching directly or indirectly, that is all different. That we'll discuss later.
so cycle is also talking about the reachability, no?
Cycle is also allowed reachability. Cycle doesn't stop you for reachability. Who said the
Yeah,
cycle will stop on reachability? No one said no.
yeah. So supposing if I want to go from C to A,
Ah,
so I can go from C to B and B to A. Then
you
this
can
is a
go. You
path,
can
and
go. You can.
uh,
Cycle never stops you that reachability. Who said that cycle stops you for reachability? No one said that.
no, I'm not saying that. No, I'm
Hmm.
saying there is another way I can go. By saying repetition is allowed. No, I can go
No,
from C to D.
another way is not cycle. Another way is not cycle. To reach that A to F, clear.
Sir, can we please move from this?
Because it is very pretty straightforward. Because why you are asking this, I don't understand. Maybe something. Maybe you can check out what you are missing out. Is it right? These are two simple concepts. Why you are taking this much time? No, maybe is it Kiran or who is that? I don't remember.
Yes, sir,
Please,
it's me.
Kiran. It is very simple concept. Why you are thinking much on it? It's a straightforward theoretical description. Okay, shall I go for next?
Please.
Okay.
Maybe some of your peer can understand. One of your friend, you can ping them. Maybe they might give you better details. Okay, shall I go?
Yes, sir, it's okay.
So now the connectedness. See here, a graph is said to be connected if there is a path between any vertices in the graph. A disconnected graph that is not connected, meaning that it can be broken into the components. See, I want to tell you, there is a graph G is existed, but it is having components. Maybe A and B is a one component. C, D, and E, this is another component. But entire of this particular A, B, C, D, E belongs to single graph only. That's what a graph is said to be connected if there is a path between any vertices in the graph. A disconnected graph is there. This is a disconnected. Connectedness means this particular graph A to B is a connected one. D to C, D to E is a connected one, no problem. But when you compare with entire one is a single graph, someone says it is a single graph is like this. Then what happens, you know, this is component one, this is component two. So that a graph might contain disconnected vertices also. You might have. They are there inside the particular graph, but they are disconnected. Such kind of conditions are there. They are called it as separate components. So here you have a next definition is there, interesting definition. A component is a connected subgraph or a larger graph because it's a larger graph. It's a larger graph. What do you say that this is a larger graph? This larger graph contains that a subgraph 1, sub G1 and sub G2, G2. So subgraph 1, subgraph 2. These two are existed in the entire larger graph. So this is a part of graph that is connected to other vertices within the part, but not connected to rest of the path. A and B is connected, but A and C is not connected, A and E is not connected, A and D is cannot connect. So what you can say that different group of people applications you want to do, like science group students are there, arts group students are there. Similarly, reason wise you want to write that mapping applications, like you geomap, if you take it, you can take that the vertices of Andhra Pradesh is one color and Tamil Nadu is one color, Maharashtra is one color, but all of them belongs to that single graph of India. Such kind of situation we want to say that component. So component means it is a part of the main graph and some vertices are disconnected, some vertices are connected. But connectedness means the graph is said to be connected. For example, you can say that this is a connected graph. Am I right or wrong? Is it connected graph or not?
Yes.
Because all vertices are attached to that single graph module. So for example, 1, 2, 3, 4, 5. So this is also connected graph. Is it right?
Yes.
Because everyone can know or reach that others. They are connected directly or indirectly. But whenever disconnected graph is there, it looks like this. A to B and C is there. This is one graph, subgraph, and D and E is there. This is another subgraph. But all these two belongs to that single graph is called main graph, that is Z. This is component 1, this is component 2. So such kind of graphs also there whenever you are implementing the applications. So hope you understand. So what is connected and whatever components is. And now the directed and undirected. Till now you have seen always A to B we said as a simple edge. So what you say that the edge can be, you can say that A to B is edge or B to A is also same meaning, no problem, because there is no directions are available. Whenever directions are there, that is called undirected graph. Whenever directions are available, you strictly say that A to B, the edge we are saying it is A to B only. We should not say B to A. We should not say B to A, because you can reach from A to B. Can we reach from B to A?
No.
No, because it is a directed. If it is undirected, either you say that A to B is no problem, B to A also no problem, because you know both directions you can traverse. A to B you can reach it, B to A you can reach it. So that's the thing you should understand, that graphs are either directed pure or undirected. But we don't have a graph like this. Some edges are directed, some edges are undirected, not in this way. For example, if it is a pure undirected, it's a pure undirected. It does not have a one directional path and rest of things are undirectional. We don't have such kind of graphs in this particular course. Maybe in the advanced algorithms, you might have a concept. So that all graphs are either directed pure or undirected pure. So that is another concept of it. Now,
Sir, are undirected and bidirected graph both the same?
no, that bidirected is both are same. We can consider A to B, there is a direction. B to A also another edge is there. Here,
Yeah.
this is called bidirection. You can have no problem. That's allowed. Clear? Yeah.
So is it the same as undirected one?
It is a directed. It's a directed graph. Bidirected graph also directed, because A to B distance is 5, B to A distance might be 7. We are not
Oh,
sure.
okay,
Even
okay.
same distance is there also different edges. We don't say bidirected graph is going to be undirected graph. No, we don't say that. Clear? It's a bidirected. Clear?
Yeah.
Yeah. So now weighted graphs are there. See, the edge we are connecting between two particular vertices, it is more interesting applications we do. The edge is not simply connected. There is a number is associated to it. The number can be distance. Some applications we can call it a distance. Someone says is a cost. Someone says is a weight. Someone says is a profit also, because sometimes to travel from a source A to destination B, what is the distance is available. So that distance we are representing with a number. So
And label.
that kind of graphs are called as weighted graphs. So the label we can say that. But weighted graphs complete concept you will know in the week 5. In the week 4, we are completely working with unweighted graphs only. We don't worry about weights now. Clear? Now, adjacent vertices. See, I want to draw a typical graph. So a typical graph we are taking a D, E. So let's do this one. This is, who is the adjacent for A means B and C. Is it right? The neighbors of the particular current vertex. This is the vertex A. Who is the neighbors for the A?
B and C.
B and C. Who is a neighbor for the E? E.
C
Who is a
and D.
neighbor? C and D. Who is a neighbor for the B? B.
A and D.
A and D. So that the adjacent vertices are two vertices that are adjacent if they are connected, direct connected by edge. So A and B are direct connected, A and C are direct connected. So they are, you can say that B and C are adjacent to A. B is having two adjacents, A and D. So that is called adjacency. What you can say that, neighbors, what you can say. Now, incidence. This is another interesting part of it. See, generally what we do is the end point of the edge is connected to which vertex. So let you take that another typical graph, whatever we have taken, B and C and D. So for example, I have this one. That's it. That's it. So here 3 edges are there, 4 vertices are there. What we do is, incident of an edge, if a vertex, one of the end point is connected or not. For example, there are 3 particular vertices are available, sorry, 4 vertices are available. We try to draw that A, B, C, D as columns. How many edges are there? Let us consider this is E1 edge, E2 edge, E3 edge. I'm just naming it. You can put any 0, 1, 2, 3, that is your choice. So E1 edge is there, E2 edge is there, E3 edge is there. Now the thing is, who is the incident vertices for E1? The E1 endpoints are connected to which vertices? Can you tell me?
A and B.
It is connected to A and B. So that, does E1 connected to A? Yes. Does E1 connected to B? Yes. Does E1 connected to C and D? No. So that it's 0. Similar way, E2 edge is there. Who is the incident for E2 edge?
A and D.
A and D. So this is 1, this is 1. Rest of them are zeros. So that's it. So a vertex is incident to an edge if the vertex is one of the end of the edge, one of the end point of the edge. Either it is connected to this end or this end. So we are connecting, we are saying it is an incident. But we are taking edge is a standard point. From the edge, whatever vertices are connected, they are called as that incidents. So definitely 2 incidents only there for an edge. Generally it happens. Now, subgraph. It's a subset of it. See, look at, for example, let me erase this. Yeah, subgraph. So from the actual graph, due to removing some edges, some removing of edges, some removing of vertices, it creates another graph. So that kind of graph, for example, you might have a connected graph like this. Maybe you have like this. So it is the actual graph, maybe it's available. So we are creating a subgraph by removing some edges or some vertices. What I did is, I removed that, this edge I'm removing, this edge I'm removing, this edge I'm removing. So if 3 edges are removed, what happens? You know, there are 2 subgraphs are created. This is one subgraph. Another subgraph is created. Oh, I'm sorry. 1, 2, 3 edges. I removed this edge, and this edge. So you will have that. This edge also I removed. So this is a one subgraph is created. This one subgraph is created. Due to removing of some edges and vertices, we'll remove it because some kind of applications are there, like minimum cost spanning trees. That such kind of applications we try to create a subgraph from the actual graph. This is the actual graph. This is the actual. After some algorithm is applied, maybe you are getting 2 subgraphs or 1 subgraph, maybe something like that. It happens. So that is called subgraph. Now, the last one is a complete graph. A complete graph is every vertex, it connects to other vertex directly, not in indirect. So this is a complete. See, whatever earlier you have shown. So if you can say this one, this is a complete. Because if this is A, this is B, this is C, this is D. Now, does C knows directly B? Yes. Am I right or wrong? Is it right? A to D? Yes. D to A? Yes. D to B? Yes. D to C? Yes. So we can say the complete graph is, in other words, they are saying that there is an edge between every pair of the vertices in the graph. Every pair. You can compare that. A complete graph, it looks like this also. Maybe, you know, another typical graph I'm giving. So this is another typical graph. It is also complete. See, I can say that it is a complete. Is it complete or not? Is it complete? Hello.
Yes.
So that complete graph is every pair of vertices, every 2 pair, a pair means it's a 2, of course. Every pair of vertices are directly connected. That is called complete. A connected graph and complete graph, please find the difference. Connected graph means, so you can start from a vertex and you can reach that every vertex is called connectedness. But whereas complete means what? Every vertex, it is connected with other pair of vertices also. Like any pair of vertices, they are connected directly. It's a direct edge. No, that means it is directed. I can say that it's a direct relation. What I mean that is. Yeah. Somebody wants to ask something. Yeah, it's a first session of week 4 only. Yeah, Sinha, you want to ask something?
Sir, is there a difference between subgraph and component?
No, it is same. You can say that, but component, what they say is basically the origin of that particular graph is component. For example, they said in the question, consider the below graph in the question. Below graph G. So they have given the graph is like this. Maybe you know A to B and C. They said it is D, E, and F. So they said this entire one is a one graph. Then we can say this is a component 1, component 2. Is it right? Is it right?
Yes, sir.
But subgraph, what happens? You know, they will give maybe connected graph is given. Already a connected graph is given. Maybe you know A, B, C, D, E, maybe something like this. Is it right? Is it right?
Yes,
But
sir.
on this, some algorithm you are executing, some process you have done. Maybe some algorithm like MST algorithm or some other algorithm. Due to that algorithm, this particular graph, it might be divided into a different graph. So what happens, you know, maybe it was created like this, A to D, B, C, E is there, but it is like this. Some edges might be gone. Maybe these edges are gone. Earlier it was there, but it was gone. Is it right?
Yes, sir.
Maybe during the subgraph, one subgraph instead of it, it might create multiple subgraphs also. Sometimes it happens because of that algorithm is applied. Clear?
Yes, sir.
Yeah.
So in the case of component, we need to take a disconnected graph always.
Correct. Disconnected collection of graphs are there. They are created as a single pool or group. We need to execute some algorithms like, you know, how many pools are there? Some algorithms are there. There you can find very good example in the GitHub notes also. I'll show you that graph. Okay.
Yes.
Yeah. So I think up to this is a conceptual. Hope you understand. Now you can see this, the logical representation or graphical representation. This is hello. Yeah. Yes, Kiran.
So, sir, can I say all complete graphs are connected?
Complete graph is a complete graph. It's a complete graph is a connected graph, but connected graph may not be a complete graph. Is it right?
Yeah.
Simple definition. Okay. Yeah. Look at this is a different kind of thing. It is undirected and unweighted graph. There is no directions are there for the edges, and weights also not given. Here it is a directed, but weights are not given. There is edge between C to E, but there is no edge between E to C. We cannot say reverse because it's a directional one. Here weights are included. Of course, this week 4 is not focusing on weights of the graph, but to know that weight better, you will know the algorithms in the next week. That is week 5. And this is weighted graph with direct edges. Like, you know, it's a directed graph with weights. Edge weights are included. There are different varieties of graphs, but in this 4th week, we always working out that unweighted graphs only. Now, this is what I discussed. Actually, in my rough work, I discussed earlier. Adjacency matrix is there. Adjacency list is there. The adjacency matrix, it is always representing a value between two vertices. The two vertices, they are saying it is I to j. But generally, I say that u to v. If there is an edge between u to v, I am representing with 1. If edge is existed. If edge is existed. U to v, u is a source and v is a destination. I am representing with 0 if no edge is available. No edges exist. That is represented by the adjacency matrix. The matrix means, rows and columns. Always the matrix is n cross n matrix. In this particular coding implementation, they try to use NumPy array, because you try to look at this coding implementation. Arrays are very easily implemented, very easily initialized using NumPy package. So Python, it is using the NumPy package, and very easily it is initializing with 0 and 1. That's what they are taking the help of NumPy. Anyway, we'll see the code walkthrough quickly. Adjacency list is there. As I said, adjacency list, how it is, it looks like, it is a dictionary. The dictionary contains key and value pair, as you know that. For example, vertex 0, it is connected to 1, 7, and 3. So what does it mean? From 0, there is a path is existed to vertex 1. From 0, there is a path vertex from the vertex 7. From 0, there is a path existed to vertex 3. For practically, if you want to go, we have an example. Maybe you can go for this. Is what example? See, I want to reduce a zoom for this. Just little bit, I'm reducing the zoom. Yeah, it could be better. Yeah, hope it is visible. Still, maybe, yeah, this is okay. Yeah, say, look at, for example, if you want to draw that adjacency matrix for this, how many vertices are there? How many vertices?
5.
5 vertices.
Good. So what we do is we try to create 5 rows and 5 columns. Maybe, 5 rows and 5 columns. Let's do that. 5 rows and 5 columns, because n cross n matrix. We try to create this. There are 5 rows. Of course, yeah, 5 it is. 5 columns you are creating. 3, 4, and 5. So because it is having that 5 vertices, so let's do that. Maybe all of them is a title 0, 1, 2, 3, 4. Similar with 0, 1, 2, 3, 4. So is there any 0 to 0 edges available? No. 0 to 1, there is edges there. Is it there or not? Is it there?
Yes, it is there.
Yes. 0 to 2? Yes. 0 to 3? No. 0 to 4? No.
No.
1 to 0? No. Because it's a directed graph. 0 to 1 is there, but 1 to 0 is not there. So 1 to 1 is not there. 1 to 2? No. 1 to 3? Yes. 1 to 4? Yes. Similar way to from the 2, if you compare, 2 to 0? No. 2 to 1? No. 2 to 2? No. 2 to 3? Yes. 2 to 4? Yes. Similar with 3 we are taking. From the 3 to 0? No. 3 to 1? No. 3 to 2? No. 2 to 3 is there, but there is no 3 to 2. 3 to 3? No. 3 to 4? Yes. Similar with 4 you are going. 4 to 0? No. 4 to 1? No. 4 to 2? No. 4 to 3? No. 4 to 4 is no. This is called adjacency matrix. Hope you got it. If there is a vertex is connected from a source vertex or some vertex, we are representing with 1. If there is no edges connected, we are representing with 0. This is simple n cross n matrix. Hope you understand. Is it right? Is it right? Now,
Yes, sir.
if it is adjacency list, if you take a consideration, so let's start that a Python dictionary. 0 we are taking whatever vertices are connected to 0, we are representing with a dictionary with a list. So 0 is having 2 adjacents, that is 1 and 2. Next, first vertex we are taking. The first it is connected to 2, 3 and 4. 3 and 4. Next, second vertex is there. It is connected to 3. Sorry, 2. 2 to 3 is there. 2 to 4 is there. So 2 to 3 and 2 to 4. 1 is connected to 3. 1 is connected to 4. Okay, over. Next, still continuing. Third vertex is there. It is connected to only 1. That is 4. And fourth vertex is there. Is it connecting to anybody? No. So it is empty list. So now you can see that the optimization of memory was done and processing is faster when you are doing adjacency list. Is it right? Is it right or wrong?
Yes, sir.
So that the algorithms we are implementing with adjacency list is preferred comparatively adjacency matrix. We always prefer that adjacency matrix, adjacency list only over adjacency matrix because of the time complexity. Because you need to traverse n cross n number of rows and columns, so it takes use time. So whatever adjacents of 2 means, simply I can go for this 2, the dictionary key value with a unit of time. From the unit of time, whatever adjacents are there, that adjacents only we are traversing. So that's very pretty simple. If not, what happens is traversing to particular row, and in that particular row you need to traverse whether 0 is connected or not, 1 is connected or not, 2 is connected or not, 3 is connected or not, 4 is connected or not. You need to check this one again n times. So that requires efficiency of algorithm. Whatever data structure you are using, adjacency list you are using over adjacency matrix is a preferred approach. So hope you got it. What is adjacency list and adjacency matrix? So you can see this one. It's a simple implementation. I'm making zoom because implementations are just a quick walkthrough. It's a syntactical and just implementation. You can see this, the same graph, what is there, that is vertices is given, edges are given. Now they want to convert into a 2D array, like adjacency matrix they want to create. What they've done is the length they are calculated, that is called size or n. I said it is n cross n, no, that's size. Here, additional package they are importing. Once imported, immediately a numpy array they are creating. The size of numpy array is n cross n. That is size into size. If 5 vertices are there, 5 cross 5 matrix is created. That matrix by default it contains all zeros because numpy dot zeros they are creating. Now wherever that there is a edge is available, we try to fix it with 1. See, I to j in E, because I to j in the E is having 2 things, a tuple values. Is it tuple value or not? It's a tuple value, no?
Yes,
First
sir.
value is
Yes,
I, second value is j. Is it right? Hello?
Yes, sir.
We are taking the first tuple value, we are fixing that adjacency matrix value of that I and j, we are fixing with 1, because if there is a path, we are fixing with 1. If there is a path from 0 to 2, we are fixing with 1. Remaining all automatically default are zeros. Zeros, you not disturb it. We need to fix it that value 1. So whatever that adjacency matrix is created, it is created like this. See, this is that adjacency matrix. So 0 to 0 is not there, 0 to 1 is there, 0 to 2 is there, 0 to 3 is not available, and 0 to 4 is not available. You could see that The last vertex, fourth row, it is not connected to anybody because it is not having any adjacents. See, it is adjacent to somebody, but it is not having any adjacents. So that's thing, all it contains is zeros. Instead of using numpy array, somebody doesn't want to use it numpy array. There is another way is a nested Python list you can create, a two-dimensional array.
Sir,
So whenever,
sir, in that A mat, sir, ij equal to 1 we have to put, or double equal to 1 we have to put.
no, equal to 1 only, assignment, no? Storing the value. 0 is
But in
overwritten by 1.
Yes, sir, but in the second second paragraph, it is written am it e double equal to 1.
Sorry. This was wrong.
Okay, sir.
So actually, okay. Sorry, actually, it's a right, but they're supposed to put if condition. Is it right? If
Okay, sir.
adjacency matrix of ij contains 1, represents that there is h.
Okay, sir.
Here, yeah. Double equal to okay, but here it is assignment. What does it mean that 1 is here? 1 represents that it is there is edge is available. Yeah. Now,
Sir, what if it is undirected?
Hello.
So if it is undirected, then
Yeah, then both edges are there. If it is undirected, maybe you can take A to B, C, and D. Maybe it's there like this. Clear? So we are creating adjacency matrix. So you have that A, B, C, D, and then A, B, C, D. So you have that 4 rows and 4 columns. Have like this. Both the things we are fixing it. By default, all of them first it is filling with 0. We don't worry about the zeros. We are worrying about that ones only. So A to A not there. A to B is there. A to C is there. A to D is not there. Now, A to B is there. B to A is there or not? It's there, no? Clear? That's it, over.
yeah.
Yeah, that's it.
So when we are creating the adjacency matrix, we have to give another condition.
Correct, over.
A mat of j of j comma I is equal to 1.
Both directions we are fixing. But how to fix the both directions, we'll see in the next implementation. Double edges we are creating. Okay. Hello. This double edge creation, how to do that is the next implementation. Clear? They'll make it double. Clear?
Okay.
Yeah. Right now it's a directional. We have a next implementation is that. See here, you have kindly raise up your hand before you're asking it out. Directly don't speak out. Okay. Yeah. Because I'll stop and come back to your screen. No problem. Yeah. See, look at here. This is nested list they are creating. They don't use NumPy. Nested list means a basic list, empty list they are creating. Length they have taken, that is called n. Now they are repeating a outer loop. In the outer loop, first they are creating a row. So see, look at that. By default, all rows are appended with zeros. That's called, particular 0th row, all columns are appended with 0. Similar way, whatever row we got it, that is copied into this. So what happens, it creates that a list of a sublist. Is it right? All zeros. Is it right? So that was happened. You look at this. By default, all zeros are there. By default, all zeros. This is what this entire job is done by NumPy. That's what we use NumPy. But somebody don't want to use it. This is another way of implementation. And this is as usual. This step is as usual. I to J, we are updating with 1. Whenever there is a path is existed, immediately the 0 is overridden by 1. So that is a directed graph. Now you see that adjacency list, same graph, adjacency list they are creating. As I said, adjacency list is a dictionary. See, the empty dictionary was taken. Once empty dictionary was taken, I have to update that each particular key with empty list until the edge is available, adjacent is available, we try to have that empty list. So what happens, you know, this 0 empty list is created, 1 empty list is created, 2 empty list is created by these lines, this one, this one. Once that is done, now we are trying to append it. Where you are appending, which particular I is linked to J, that J we are appending into I. So what happens, you know, if this particular, this 0, if it is connected to 1, immediately 1 is appended. If 0, it is connected to 2, 2 is appended. Hope you got it. Is it right? So that appending job is done by this particular one. This is. So creating that adjacency list is very easy. See how particularly, and it looks like very clear and neat. So 0 is connected to 1 and 2. 1 is connected to 3 and 4. So we can say adjacents. What you can say is 2 is having 2 adjacents, 4 and 3. 3 is having 1 adjacent, but 4 is not having any adjacent, so that its empty list remains. So that's simple. Now, as you asked that, unweighted and undirected graph. Here there is no direction. A to B, like 0 to 2 there is edge, means 2 to 0 also there is edge. So that we should double it. That's what they have done this code. You can see that interesting code here. See here, same vertices, same edges they have taken. And here, interesting way what they did is, see here, already existing E plus there is another thing they are creating. So 0 to 1, it is reversed, 1 to 0. Is it right? Another list of vertices are created. Am I right or wrong? This list comprehension, what it will do? I to
Yes.
J is there, J to I will be done. So what happens, you know, this list is, another list is added for this, 1 to 0, 0 to 2 is there, no, 2 to 0, 1
3,
to
1.
3 is, you know, 3, 1. So like this, you are getting a double of edges. So that is called UE. UE is going to be double of E. Whatever edges are there, the edges are updated with undirected edges. Hope you got it. And rest of the process is same. Whatever process you are creating, the matrices, 0 matrix you are creating, the edge weights you are fixing, that I to J you are fixing it. So that is happened exactly the same. So whenever undirected graph is there, earlier 4 is not having any adjacents, but now 4 is having 3 adjacents. You can take a look, because 4 is connected to 1, 4 is connected to 2, 4 is connected to 3. See here, because 3 to 4 is there, means 4 to 3 also there is a adjacency is there. So this is double. But interesting thing is, this double comprehension you must know. Existing edges, we are reversing U to V and V to U, and we are doubling the edges. That's it. Over. U to V I say generally, but here they are saying I and J, J and I. That's it. Yeah. If you are implementing with nested list, yeah. Yeah, Kiran, tell me.
Sir, instead of using the list comprehension to append, to add the reverse of tuples, like what we can do is we can remove the third line, and in the loop we can say a mat of J of I is equal to 1. Then the time complexity will be reducing.
No. First remember whether it is, if A to B is their edge, means B to edge also consider not. You might have a traversal, no? Always there is no guarantee, always we traverse 0 to 1. You might start traversing from 1 also. Is it right? Is there any rule you must start from 0?
Yeah.
No, very simple. Is there any rule always the train should be start from Delhi? No rule, no. Anybody can start from any source, right?
Yeah.
So in that case, everyone should have that adjacency. Like A is adjacent to B means B also adjacent to A. Clear?
Yeah, that is fine.
Then how can you reduce complexity? Tell me. I don't understand.
I'm saying we can remove the third line, and in the for loop, what can do
What do
is
you want
in
to
the
do in the
second
for loop? Tell me. How can you make it double?
no, in the second
Second for
for
loop, what do you want to do?
yeah, for I comma j in E, I after A of A mat of I of j is
Here
equal
is
to
append you
1.
want to do. Append you want to do here.
No, in the second for.
Second for means this one, no?
No, third for.
This one.
Yeah, after setting A mat of I of j equal to 1, I will
This
say
one. This one. This one. You are talking about.
yeah, after
Tell.
setting A mat of I of j equal to 1, I will say A mat of j of I is equal to 1.
Okay. You want to do that A mat of
J
J
of
and
I is
I
equal to
and wait.
1.
Let me try that because I'm not sure. Maybe you are right.
J
This is
is equal
also
to
one.
1.
Two initialization you are doing. Clear?
Yeah. Then
So now
we
let
don't
me
need
let me
to.
let me check it. Let me check it. Maybe this edge you are getting 0 and 1. Okay. So 0th row and first one, so that 0 to 1 you are fixing it as this is 1. Okay. And immediately another initialization you are doing. Okay. 1 and 0 also. Yeah, it is okay. Fine. Great. This is a good kind of thing. Because instead of making double, we try to do two initializations at a time. Yeah, cool. That makes interesting. Kiran, thank you. So then
Yes.
you need not do this kind of double. Is it right?
Yeah, that is what I'm saying. We can
Correct.
remove the.
You're right. You're right. Perfect. Then you need not double the edges. Right. Yeah, it's a good one. Yeah, good idea. Thank you. So similar lines, the adjacency list representation also. So if you could see that adjacency list, here also they are doing a double. Now instead of making double, I'll get back to the doubt. Wait. Instead of making a double, what we do that A list of that I is append, A list of J also append I you can do it. Am I right, Kiran?
Yes, sir. Here also we can.
Correct. Here also you can write another append statement. Instead of I is appending J, we do that J is appending I. Yeah, that makes interesting one. Yeah, Sandeep Kumar, you want to ask something?
Yeah. He suggested the statement for what exactly? Because
No. He doesn't want to use another memory space like complexity. Why it is, this space complexity you are increasing it as well as one iteration you are running. Is it right? Why to use the additional
okay.
space, double of edges? Simply, he doesn't want to do this one. Clear? This step, what I'm highlighting. Is it visible?
Okay.
Undirected graph means whenever A to B there is edge, B to A also there is edge. 0 to 1 there is edge means 1 to 0 there is edge. Is it right?
Understood.
So this input is double. How can it make it double? By using this statement. Is it right?
Correct.
We don't want to do this one because it's a waste of memory space, right?
Okay.
So simply another statement we add after this one. So what another statement is? A mat of J and I is also 1. So I to J is 1, J to I also 1. Over. Clear? Hello?
Correct, but U is dealing with the list, A mat is dealing with the matrix. So for matrix, we have to explicitly do only, no?
No.
Adding.
Matrix, this matrix code we don't remove. This is as it is.
Correct. So this
But
is
this part is not required. No, is it right?
Hello.
Hello. Yeah.
But sir,
but
loop is working in UE.
In this only you're working. Okay. Oh, we'll change it. We only will change it. What is that?
Oh.
Over. Clear?
Yeah, now fine.
That's fine. Maybe UE I did not identify. Okay.
Sir, It should be A mat I J and A mat I J I, sir. What
Correct.
we should do?
Two initializations, A mat I and J. I is
No.
adjacent to J is true. Clear? J is adjacent to I also true. Is it right?
Yes, sir.
See, I think, see, E is already existing. Okay, so E we don't have to worry about.
Correct.
So E is existing means there is a tuple called as I comma J in E.
Correct. This is.
So I think the existing line is wrong. A mat of ij, instead of that we can straight away write if ij is there, a mat of ji also is equal to 1.
Two statements.
Only one? No, two statements are. Ij is already existing, no, in the E.
No. See. The matrix is like this: 0, 1, 2, 3. 0, 1, 2, 3. Clear? Okay. We are fixing 0 to 1. There is a path. Clear? Okay. How can I fix 1 to 0 is a 1? How can I fix it? At the same step. This one also has to be changed from 0 to 1. Is it right? How can I change it? By using this step only, no? Is it right? 0 is adjacent to 1. 1 is also adjacent to 0. How can you say that? So somebody is in the call who is asking about it?
Yeah, I am in the call. Not getting what we have solved here exactly. Because
no.
First part is dealing with the lists. And
No.
creating UE is mandatory, no?
Wait. This one you are talking about. Is it right? Adjacency
Yes.
matrix for undirected graph. Is it right?
Understood.
This is clear?
Clear.
I think we can avoid this one by whatever Kiran said by using it.
Yes, we can avoid.
Yes, we can avoid.
Fine, no problem. Now we are coming to adjacency list. Sorry, this is a nested list. Sorry, nested list also same. No, is it right? No difference. NumPy array they are using, here we are using nested list. This is also can be avoided. Now we are going for adjacency list. Is it okay?
Yes.
I'm talking about adjacency list. Adjacency list also what it will do is here E you are taking. Is it right?
Yes.
Hello.
Yes.
Yeah.
Yes, sir.
So now already empty dictionary was created with empty lists. This key is available, but values are not there. Is it right? Now what I did is a list of I is append with j, so that if 0 is adjacent to 1, so immediately this 1 is appended. Similar lines, I'll write one more line here. Adjacency list of j is updated with I. Is it okay? Another statement. Then what happens that whenever 0 it is having adjacent of 1 is appended with 0. Is it right?
Yes, completely right.
Yeah, it's over. Simple. That's it. Yeah.
See,
because
but there is a chance J, the key named J might not have been created yet. So append will not work.
No. All keys are created by using adjacency list. See, adjacency list you are taking by length. Is it right?
Okay.
Is it by length or not?
Yes.
So then no problem, no? All keys are created.
Okay, understood.
That's over. Yeah. Okay. Up to this is clear?
Yes, sir. Sir, in a dictionary, this membership operation is not much costly, right? So
correct. Unit of time.
Yeah. So in the second for loop, if we're going through the each new I, if I check if the I is not in the A list dictionary, then I will set it. I will initialize in the second for itself. I can remove the first for.
Correct, correct.
And if it is already present, then I can append. Then I think we
Correct.
can remove the first four.
Which for loop?
And
No, this is required. No, this is definitely required.
yeah,
Whenever vertex
suppose
is there, that vertex key should be there. Am I right or wrong?
yeah, initialization also we can do at the same time. No, if I
Initialization means empty, empty list you are initializing. Which one do
yeah
you want to initialize?
yeah going through each edge. If I is not in the A list dictionary in the adjacent
Hmm.
list, then I will
Hmm.
initialize. If it is already present, then I will append.
Yeah, yeah,
I'll do the
that way
same.
also you can do. That also you can do it. Like if condition, you can check it in operate and all.
Yeah, in the second for itself, I will do both initialization and
Yeah, both
append.
initialization and appending you can do. No problem.
Then the time
Okay.
will maybe
Yeah,
will
yeah.
be reduced.
No, that's no problem because this for loop, both are different. Complexity is concerned of the highest space with a complexity, right? Right.
Yeah.
So here the most important thing is additional space we are avoiding, right?
Yeah.
Yes, space complexity can be reduced because of double you are reducing, so that space complexity can be reduced. But time complexity, even you remove this one also, it is O of n complexity only, right? Yeah. Okay. Yeah. Just give me 1 second. I'll get back after 2 seconds or 3 seconds. This is all theoretical and practical implementation of converting your graph into digital data like zeros and ones. So like adjacency list and adjacency matrix. Now let's do some kind of algorithms in the graph. Just give me 2 or 3 seconds. Okay, I'll get back. Yes. So hope you got it. Up to this is okay. Shall we go for the next?
Yes, sir.
Now, so as I said that beginning of the session, graphs are non-linear data structure. So it is a non-linear one. So basically I said it is traversing of data in the graphs is going to be a non-linear. It's not a sequential one because it's unstructured. Basically, it's not having any structure. Just combination of vertices and edges are available. Now, there is basic traversing techniques of the graphs is the breadth first search is there, traversing algorithms. See, mostly code is just a walkthrough. We don't worry about that. Just only quick walkthrough. We should understand the concept. That's what first we are working with, understanding the concept. So traversing a graph, it includes basically two graph algorithms are there. The first one is that BFS. So breadth first search. Breadth first search. So what we are trying to do is, whenever a vertex is traversed, and it's all adjacents are traversed, whatever next available set of vertices are there, all are traversed. For example, A is traversed, then immediately who are adjacent to A, we try to complete that particular traverse. After that particular adjacents are over, then we take another vertex and then we try to traverse that. So the next level of it. What we can say is adjacents is nothing but, as I said, it's a neighbors. So what we do is any vertex or current vertex and it's all adjacents or neighbors are traversed. So that is called BFS. So let's take one sample graph. I'm taking one sample graph. Maybe it could be a simple or different graph. I'm taking A B and C and D and something like E, F and G, maybe some kind of random. So we are having this particular graph. B is connected to both of them. Of course, I've connected here. C is connected to Z and D also connected to Z. Some kind of, a random graph. Now, let's start that traversal from A. You can say that this could be a traversal source. Of course, you can start from any vertex. That is your choice. But whenever we start it from a source, the source vertex is traversed, and who are the adjacents of the source also traversed. Currently, A is starting vertex. Let you consider. Who is the adjacents of A? Who is the adjacents of A?
B, C, D.
So that your BFS traversal, what it will traversal procedure is, first it might traverse A, and who are the adjacents of this A? Maybe B, C, D. So what happened, this level 0 is over, then level 1 is over. Is it right or wrong? Is it right? Is
Yes,
it right? Then, so A is over. Of course, I'll use a green color once this is traversed. Then A is having 3 adjacents, B, C, D. After that, B is having 2 adjacents. Is it right? B is having 2 adjacents or not? Hello?
Yes, sir.
So that B next to 2 adjacents are E and F. These are traversed. Once these are traversed, C, whatever adjacents are there, it tries to traverse it. What is the C adjacent? So that
G.
these two are traversed. G, so that G is traversed. Once G is traversed, so what is the adjacent of this particular D? Is there any adjacents are there? G, but it's already visited. Is it right? Is it right?
Yes.
So that no further traversal here, traversing is closed. But remember, if a graph is available, there may not be only one way of BFS traversal. If you consider same graph, you might have another BFS traversal also, like A is first. It's not the rule that left to right should be traversal. Maybe you have next, once this level 0 is over, then it comes to that level 1. When it is coming to level 1, it might traverse D, C, B also. Is it right? Is it right or wrong?
Yes.
There is no rule that B, C, D. There can be D, C, B also. And similar lines, whenever you are coming to the B, or whenever you are coming from right to left, you are traversing. What we do is D adjacent is available, G might be traversed. After that, C is not having any adjacents over, B is having 2 adjacents are there, F and E. So that's the reason, even in the lecture, in the graded questions, whenever we give the BFS traversal or DFS traversal, we clearly say that if the edges are available in the BFS, always the BFS will choose that chronological order or sorted order of that vertices, so that no confusion. There is no rule that right to left or left to right. Only we prefer that chronological order. If it is chronological order, this particular traversal is correct. Am I right or wrong? Hello? Is it right?
Yes.
Yes.
That note also they will give it, because if a BFS traversal you are doing on a graph, there might be possibility of multiple BFS traversal possible, because there might be left to right or right to left or in the middle vertex. There is no rule that always it is left to right. To avoid that confusion, generally in the question they'll give it. So the vertices in the BFS traversal are traversed in chronological order or increasing order, so that the pretty sure the traversal is we are getting clearly. Now the situation is how this algorithm it works. How that algorithm it works. So the thing is, it is taking the help of Q. What it is taking? It is taking the help of Q. So I hope you know that the implementation also. Just I'm going. Just you can see it. See this part only I'm going. I don't want to go for the coding part because coding part is very easy to understand. You can check it. Choose a starting vertex node and add that NQ into a queue. We are trying to add that particular one into the queue. Then mark it that starting vertex as widgeted is a true, because we try to maintain that widgeted status also, whether it is widgeted true or not. If it is widgeted, we mark it as a true. Next one. While queue is not empty, we try to repeat it, the iteration. Inside the iteration, we dequeue or delete from the queue. Always, of course, you know, queue is always first in, first out. Whatever first input one, that is first output one. So whenever first in, first out one is done, whatever you got it from the queue, then each dequeued, whatever adjacents or neighbors are there, if they are not widgeted, mark them as widgeted and enter into the queue. So we mark them as a widgeted and we are doing that enter into the queue. We repeat the same process until my queue is empty. So if you could see that the same graph, let's take a queue. We are taking a queue. Maybe you know the queue, it looks like this. Empty queue. This empty queue, what it contains is, as and when the starting vertex is there, that might be, you know, this particular one is starting source. We are marking this widgeted is a true. Is it right? Widgeted is a true, no? Is it right?
Yes, sir.
Immediately we are adding this A into this particular queue. We added. After adding, what we do, we are trying to repeat a iteration. What is the iteration? Until my queue is empty, we try to remove whatever that first in, first out one is happening. What is the element available in the queue? It is A. This is removed. It is removed means it is coming out. Once it is coming out, whatever adjacents are there, all adjacents also marked as true. They are marked as true. After marking them as a true, we try to add them into the queue. B, C, D. After adding B, C, D, what we do? We try to remove it. Who is removed next? Who is removed next?
B.
B is removed.
Yes. So B is removed. Once B is removed, whatever that adjacents of this B is there, they are marked as true. Once they are marked as true, immediately they are added to here, so that E and F is added. Once E and F is added, next removed one is what? What is the next removed one?
C.
C.
Correct. C is removed. Once C is removed, who is the adjacent for the C?
G.
Correct. So G is marked as widgeted. Immediately that is also added to here. Next, D. So D is next removed. After removing D, any unvigneted vertices are there for the D neighbors? No.
No, sir.
So that simply D is removed. No adjacents. Simply E is removed. No adjacents. Simply F is removed. No adjacents. Simply G is removed. No adjacents. All adjacents are over. My queue becomes empty. Immediately my iteration stops. That's what. Repeat that steps 3 to 4 until my queue is empty. Now you can see the implementation. See here. So here already this code implementation, you know, in the week 3. Everybody knows that how the week 3 code is there in the queue. The NQ operation and DQ operation. We don't worry about that. Here, this is what the BFS list algorithm. See, remember once again, I'm telling you, almost every time they try to use adjacency list only. They don't want to use adjacency matrix. Using adjacency matrix is again, complexity is more. Always you also prefer that adjacency list only. See, look at it. They are taking a BFS function. It takes that adjacency list as a parameter, starting vertex which you want to start the traversal. Empty widgeted dictionary is created. By default, all of them marked as unvisited, so that essential list of visited dictionary is false. Initially, no one is visited. Then Q object is created. Already Q class is there. The object is created. Once it is done, the starting vertex, whatever you have chosen as a parameter, that starting vertex visited value, whatever false is there, that is changed into true. As I said, starting vertex, we mark it as a true. Once it is marked as a true, it is added into the queue. That is called NQ operation. Once done, we repeat this set of statements until my queue will become empty. So in this, we are dequeuing the first element, whatever element is available, that you are getting current vertex, that is A. Once you got the A, then in the adjacency vertices, whatever the current vertex is there, in that which of them are not visited. In that which of them are not visited, that one we are marking as a true. So what A we are pulling out from the queue, and whatever adjacents are there, all of them we are marking as a true and adding them back to the queue. So as I said, that the queue is extending. So next one, what happens, next front element is removed from the queue. So after the next front element, whatever adjacents of this particular, the front element is this, the next front element is this, B. Whatever adjacents are there, they are visited and then they are marked. So that is continuously done. After all this, my queue will become empty. So this condition will become false, and as well as all of my visited matrices or visited adjacents are become true. So finally, we are returning that visited status. Visited status means all of them are true. So all of them true means simply all are visited. All of them are visited. Hope you understand. It is taking the BFS algorithm, taking the help of another data structure called Q. Is it clear? Is it clear?
Yes, sir.
Now,
Sir, once again, can you tell me, sir? Because it is confusing, that Q portion is some confusing, sir.
See, Q is always first come first serve basis. Is it right?
Yes, sir. Yes, sir. Yes.
Whatever first element you are adding, that element is removed first. So here, whatever first visited. So first visited is this A. So this A, immediately it is added into the queue. So this is my queue. Does my queue is empty? No. When queue is not empty, we are removing this from the queue. Whatever adjacents of this particular A is there, that is added. Whatever adjacents are there for A, who are adjacent for A?
B, C, D, sir.
Correct. They are added here. C, D. And they are marked as visited also. Visited. Clear? After that, who is next removed one?
B, C, D.
No, B. First remember B. Don't say that B. So B is removed. Once B is removed, so who is adjacent for the B?
E and R. Sir.
They are not visited, no, so that they are marked as visited. Immediately they are added. Once they are added, C is removed. C is having one adjacent. Is it there?
Yes, sir.
That is also marked as visited, and that is also added. Now, what is next removed one?
D, sir.
Correct. When D is removed, does D is having any unvisited vertices to be visited?
No, sir.
No. So that no more adding into the queue. E is removed.
Yes.
Then F is removed. Then G is removed. Once G is removed, my queue will become empty. That means that entire graph is traversed.
Yes.
Yeah.
Yes.
Now, I think somebody,
Open the code, sir.
Kumar, you
Last
can
part.
mute, who is that speaking?
Yes, Basant, sir.
Yeah, Basant, tell me.
Open the code, sir. Last.
I'll open the
Yeah,
code. I'll open the code. No problem. Yeah. Here is the code.
Yes, just in this one list key key of just note 2, sir. Note 2 adjacent of note 2 4
Hmm.
and 3 that is
Hmm.
given.
Hmm.
This should be in chronological order. 3 then 4
No, it's a
here.
first come first serve basis. See, in this particular vertices, whatever you are sending, see, look at here, see, look at 0, 1, 2 is there. Is it right?
Yes, this is
So
correct
yeah,
order.
here, this order only. This order only it will maintain. First 0 is visited. Who is the adjacent for 0? 1
1
and
and
2.
2.
Yeah, those are traversed. So what you can say is 0, it is connected to 1 and 2. Is it right? Next 1 is connected to 3 and 4 because this is the input. Is it right?
Yes.
2 is connected to 4 and 3. 2 is connected to 2 is connected to 4 and 3 also. Is it right? Okay.
This should be in
Wait.
chronological order.
Wait. Let me complete. Now, as per input, I'm talking about 3 is connected to 4.
Yes.
Is it right?
Yes.
This is the graph now. This is the input. Is it right? Now,
Yes.
my queue is created in this way. My queue is created in this way. First queue is added with 0. Is it right? Because starting vertex you have given 0, no? Okay. Hello. Yeah. So this is
Yes.
visited.
Are you listening?
Hello. This is starting vertex, no? Here, look at.
Yeah.
Hello. So that this is marked as
Yeah.
true
Yeah.
and added into the queue. So once it is added, it is removed. Who are adjacents of 0?
1 and 2.
So 1 and 2 are added. As per that input only, it is added into the queue. Okay. Now, so after that, this is true because visited. After visiting, what is the next element is removed? This one. Is it right? From the queue.
Yes.
Who is adjacent of 1?
3 and 4.
Correct. 3 and 4. After 3 and 4 is done, so next removed one is what? 2. Is it right?
Yes.
So 2 is removed. But after 2 is removed, this 3 and 4 is already visited. They are already available in the queue. So that just remove. No further adjacents for the 2. Is it right?
Yes.
So simply it is this. This no problem. Now that
Yes. Okay,
particular
sir.
thing, yeah. It is always input. They try to give it only, but conceptually when they're asking quiz questions, they try to give this note also, so that to avoid this confusion, this coding implementation, simply they'll give it. If the graph is given in this way, like they try to give the graph like 0, 2 is here, 1 is here, 3 is here, maybe something like this. Then they clearly say that always chronological order. So first this is visited, then this is visited, then this is visited. Yeah, pretty clear. But this input is very clear. Yeah. So please, this similar kind of approach, but adjacency matrix is used. I don't concentrate on adjacency matrix because it is the additional thing. Now the situation is, you can see that, yeah, here it is. The complexity concern, you can see that the complexity concern is whenever adjacency matrix you are using, it requires that O of V square. V is nothing but the number of vertices in the graph. If you are going that adjacency list, the complexity it is very good efficient. That is O of V plus E, vertices and number of edges. So that always we try to prefer that adjacency list only. We don't prefer that adjacency matrix, but it's another figuring out that using adjacency matrix. Now there is an interesting application. See, look at here. The application is finding the level number of vertices using BFS. See, I want to go over, because I don't want to walk through the code. Just I want to make you to understand the concept, what really this application, one of the application of BFS is. This is one of the application of BFS. This is finding level number. Is it level number? Yes, level number. Finding level number. See, look at, maybe you take some random graph. I'm taking some random graph like this. 0, 1, 2, 3, and 4. Maybe, you know, it's a kind of a random typical graph. Always, I try to use a typical graph. Maybe sometimes, you know, using a typical graph, you might struck or you might find something incorrect or correct, maybe something like that. See, look at here. Let's start that the traversing from this source of this. My question is, what is the level number of this? Is it level number of which level it belongs to?
Zero,
It could be
sir. Zero.
zeroth level. This is zeroth level. This 1 and 2 belongs to first level. Is it right? Is it right?
Yes.
These 3 and 4 belongs to that second level. I want to identify this level numbers. Maybe they'll give it a complex graph. They will ask you that, can you identify that level information, which particular vertex belongs to which vertex, which particular level, by using starting vertex as a sentinel marker. Starting vertex is this, because starting vertex only considered as a 0th level. From that, you try to find out the level numbers of all. So it can be done using that, you know, the BFS algorithm. So it is pretty straightforward. So what we can do is, initially we try to allow.
Sir.
Yeah,
Sir?
tell me.
If 0 and 3 are connected, sir, then what?
If 0, 3 are connected, then that level of 3 also it is first level. Clear?
Okay.
Yeah. So here, look at how to do that is very simple. We try to record that length of that, you know, distance from 0th vertex to first vertex. How many edges are length available? So 0th vertex to first vertex, the length is available with one edge only. They are connecting. Is it right? Is it right? 0 to 1. How many edges are required to connect? It's one only. Similar with 0 to 2, directly we are connecting with one edge. So that we can consider it's a level number is 1. This level number is 1. How many edges are required to reach from 0 to 3 is 2 edges. Is it right? Is it right or not?
Yes, sir.
So that's what, like this way you can reach this. So here the level number we are giving is 2. Similarly, to reach the 4, 0 to 2, 2 to 4. So it is also level number is. So the simple thing is, we are trying to find out the shortest path in terms of edges. How many edges we are using to reach that current source to other vertex. The similar logic is applied. You can see this one. See, finding the level number. This part we don't worry, because this already, you know, Q, we are doing NQ operation. Here, please look at here. Oh, sorry. Actually, two different applications they combine. Parent information also they want to maintain. Sorry, I have to put the parent information. This is the level numbers. Who is the parent of 0th vertex? Because two applications. One is finding level number. Second one is finding parent information also. Who is the parent of 0th vertex?
No one.
No one. Can you say the -1? -1? Clear?
Yes.
Yeah. Now, who is the parent of this 1 and 2?
0, sir.
No. Yeah, it's 0. Correct.
0.
0. The parent for this one is 0. The parent for this 2 is 0. Who is the parent for 3 and 4?
1 and 2, sir.
So this parent information for this one is 1, because this is the parent information for this one is 1, and the parent information for this one is 2. This is the parent 2, this is the parent 1. Yeah, that's okay. Fine. Okay, this parent information also I want to grab it. So that is also directly they did it with BFS Travers only. See, they have taken 2 dictionaries in this line number, empty dictionaries. Initially, both level number and parent information also -1, because basically we don't know, no information is available. Simply the key value they are fixing is -1, because everyone is fixing with -1, -1, -1, -1. So every particular vertex is having 2 -1s are there. Q object is created as usual, which you have done it for BFS traversal. The starting vertex they have taken as 0. This is what starting vertex, because already I said 0th vertex you choose it, or anything you can choose it. Now adding the element of the starting vertex into the queue, that's earlier we did it. Similar things you have done. Now until my queue is empty, because already first vertex is available, so we use that one only because my queue is not empty. The 0th vertex is there. Removing from the queue, we are trying to get it from the queue. Once we got it from the queue, whatever adjacents of the current vertex are there, if the level number is -1 is there, if that level number is -1, so -1 means level information is not updated. Once it is not updated, what we do? Level number of the current vertex +1. Already -1 is there. -1 + 1, what happens? 0. Is it right? Is it right or not? Hello? Hello? Am I in the call?
Yes.
Yes, sir. Yes, sir. Yes, sir.
Yeah.
So what happens, what happens, here -1 is there. Here also 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 -1 is there. This is the current vertex. Is it right? Current vertex or not? Hello? Hello?
Sir, how
Yes.
come?
Yes.
Sir, how come?
Current vertex is this. See, adjacent vertex of the current vertex. Current vertex is already removed from the queue. Is it right? Because already recent one is there. Is it right? Who is the recent one? 0th vertex or not? Hello?
Yes,
Hello?
sir.
So whenever
Yes.
current vertex is there, the current vertex value, current vertex level number is there, that +1. So what is my current vertex level number? -1. -1 + 1, what happens? It will become 0. Is it right? Hello?
Yes, sir.
So that what happens, immediately this current vertex, I'm sorry, adjacent vertex is -1. I'm updating that current vertex of the adjacent vertex. Yeah, sorry. Here already 0 is updated. I'm sorry. This one I forgot. Initially they put it current vertex level. Sorry, I'm sorry. I want to take a different colors just to avoid what I'm trying to say, that this, 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 this. Okay, this is pretty clear. This is pretty clear. This is clear. Yeah, up to this is okay. Now the thing is, there are 2 properties we want to investigate. Parent information we want to investigate, level number also. Both of them initially, all of them -1. So that I want to get at -1, -1, -1, -1, -1. This green color we want to represent that parent information, and red color we want to represent that level information. Is it okay? Is it okay? Hello?
Yes.
Is it okay? Yeah. So now we are trying to do that initializing the level information of 0 is 0. What happens that this particular -1 will go, 0 will come. Is it right? Is it right or wrong?
Yes, sir.
Hello? Now, current vertex is this. Is it right? The current vertex adjacents are there. See, whatever the current vertex adjacents are there, that each adjacent you are getting from that, if that level of that adjacent vertex is -1, we try to update the current vertex value +1. So what happens that this level number of the 0 +1. So what happens? This level information will come to 1. This level information will come to 1. Am I right or wrong? That is updating. Current vertex adjacents are updated. The level information is current vertex level information +1. Hope you got it. Is it right? Hello. Now,
Yes, sir. Yes, sir.
now the next one is there. Parent information is there. See, look at here the parent information. The parent information of the adjacent vertex is updated with current vertex. So current vertex is this. The adjacent vertices 2 are there. The parent information we are updating with green color. So the green color is, it is updated with, who is the parent of the first vertex? -1 will go. Who is the parent of the first vertex?
0.
0.
So that. Who is the parent of this one? It is also 0. It is updated. So now this particular NQ, it adds that adjacent vertex. Adjacent vertex means as usual. First it is 0 is added, then 1 is added, then 2 is added, then 3 is added, then 4 is added. So that when that next it is repeating means what happens is next DQ element. Who is the next DQ element? Already DQ over. Next DQ element is 1. Is it right? Who is the next one?
Sir, 1 second. Where is V being decided? Like, what will be the V? Where is it being decided? We have a line, no? Level of V is equal to 0. So,
No,
who is
you are
deciding which
talking
V
about
to take?
level of adjacency vertex is current vertex.
No. Just before first NQ, we have written
this one.
No, top, sir. Little bit
Okay.
up.
Okay.
No. Level of V is equal to 0. So where is V defined?
It is starting vertex. They have given as a parameter. This is called
Okay,
here.
as a parameter. Okay, understood.
Okay, yeah. You can start it from any vertex, but they have chosen 0. That's it. Simple understand. Yeah.
Okay.
Now that parent information is updated. Next it is repeated the same. Whenever repeated the same, next it is current vertex, it goes to that 1. Whenever it is going to the current vertex is 1. If it is current, who is adjacent for the 1? 2 things are there. 4 and 3 is there. 4 and 3 is there, no? Is it that 4 and 3? Yes. So whenever 4 and 3 is there, particular level information is updated. Current vertex level information +1. Current vertex level information is already 1. So 1 + 1, it will become 2. This one will become 2. Is it right? Red color indicates level information, no? Now, still we are going with parent information. But parent information is what we have done is the parent of adjacency vertex is current vertex. See, I'm sorry. Actually, this parent information of 4 also updated with vertex 1, because immediately BFS what it will do, all adjacents of 1 is finished. Is it right? Hello? It's a BFS. Who is the parent of 4 means the parent of 4 is 1. So it is updated with 1. Who is the parent of 3? It is also 1. Hope you got it. Earlier I said the parent of 4 is 2. No, it's not. It's wrong. Because once 1 is visited, all adjacents of 1 is traversed. All adjacents means they are children of 1. So this information finally you are printing. See, look at here. The first one is that level information. 0th vertex level number is 0. First and second vertices level number is 1. third and fourth vertices level number is 2. But 0th vertex is not having any parent. So -1 remains as it is, because even you check it, my green color of this particular parent information is -1 only, because 0th vertex is not having any body, any parent, because that's the first vertex. And now the parent of this particular 1 and 2 is 0. The parent of the 3 and 4 is 1, because it's a BFS. So who are adjacent, immediate adjacents, they are going to be processed. So this is a simple kind of approach, but I strongly recommend you first you understand the concept, digest the concept. Don't by heart the code. By hearting the code is a very dangerous one. Sometimes you lose it. So always you remember the process. All are initialized to -1. We try to pick up any starting vertex. That starting vertex, you're trying to update that the vertex level number is 0. Who are adjacents you are picking up? That adjacents level number is updated with current vertex level number +1, and parent information is updated with current vertex information to the adjacent vertex. That's over. So that's pretty simple. Maybe just you remember the concept and just you can recollect. So is it clear? Yeah. Now, am I in the call? Hello. Yeah,
Yes,
because
sir, you're audible.
yeah, cool. Yeah, it makes sense. So now that DFS we are going, depth first search. See, I don't directly walk through the code because before understanding, without understanding. So let's go for that. Another traversal algorithm is DFS. So it's a depth first search. Depth first search. We go towards the depth of it. So to use this depth first search, we try to use that a data structure called stack. Of course, either you use it that any user defined class, or somebody can use it a recursive kind of approach. That's also okay, no problem. But typical way, I try to take one sample graph and then we try to process it, what way it is processing is going on. So let's take a graph, maybe a kind of a typical graph, 0, 1, 2, 3, and 4, maybe something like this. Maybe same graph I'm taking, but the interesting traversal, you can find it here. So this was the thing, and here it was there. Yes. So let's consider this is the starting vertex or source. So as I said, it is using a stack. So stack is always, it is in the LIFO data structure, last in first out. Let's consider my stack. It looks like this, because it's a one side entry and one side, same entry of and same exit, whatever entry point and same point of your exiting, that might be top position. So whenever you found it, the starting vertex or current vertex, immediately we try to push it. Of course, you mark it as a visited and we try to push it. So once it is pushed, like, it is marked as visited and it is pushed. So after that it is popped, maybe, it is popped out. And once it is popped out, it is marked as that visited. And who are the adjacents of this particular visited one? They are going to be pushed. Who is the next adjacents are available? 2 adjacents are available. So that is first adjacent might be 1, second adjacent might be 2. Maybe 2 and 1 also you can do it. That's not a problem. Now, immediately 2 is popped up. Am I right? 2 is popped or not? Because 2 is the top
Yes,
one, no? So that this is marked as visited. Once it is marked as visited, what the adjacents of the 2 is available, they are pushed. So already 1 is available. Then the recent 2 adjacents are there, 3 and 4. Maybe 3 and 4 might be pushed like this. Maybe 3 is pushed first, 4 is pushed next. After pushing that, so next it is visited one is this one, because it is popped one next. So 4 is visited. So please quickly remember, you are going towards depth. Am I right or wrong? You're going depth or not? Are you going depth?
Yes, sir.
So now, after 4 is pushed, 4 is having any adjacent, because already this is available and available in the particular stack. We don't have any further depth. We don't have any further depth, no? No problem. Next popped one is, because already 4 is popped, 3 and 1 is available, 3 is popped. So that this is also visited. After the 3 is out, it is popped out. Last one, it is 1. So 1 is popped out. Once 1 is popped out, it is visited true. So depth it is going in this way. See, interesting path is 0 to 2, 2 to 4, 4 to 3, 3 to 1. It is going vertically. Instead of going horizontally, breadth, it is going vertically because of the stack. So you can take a look of this implementation. Yeah, this is maybe, create a stack. So set that visited and keep the track of visited nodes. Push the starting node into the stack. While stack is not empty, pop that each element U from the stack S. If U is not visited, mark it as visited. Once it is visited, perform any processing on the node, whatever it is there. Get all unvisited neighbors of the particular U and again push them into the S. So repeat the same steps of 3 and 4 until my stack is empty. So that is what happened. So you can take a look here that earlier implementation of week 3 only they are using. Whatever you know the implementation of it. Of course, maybe next implementation is that it requires only recursive approach. That approach is simple. Maybe coding length you can reduce it. And one more thing, if they want to ask in OPP examination BFS or DFS question, this code is prefixed given to you. You need not write this code. That is for a kind information. Hope you got it. What I'm trying to say, because somebody might fail it. If I want to implement a DFS algorithm, stack code also I need to write. So no need. In the OPP examination, what we give is, we always give it a pre-implementation of stack, a pre-implementation of queue. You can use them without rewriting. You're supposed to write only that DFS algorithm only. You need to write only BFS. Yeah. So here, the adjacency list is taken as starting vertex. Of course, there they have taken as a V as a starting vertex. Here they said it is start vertex. Visited they have taken is empty, because by default visited is false. That's what they have done. False is done. Now the stack object is created. So then the first starting vertex is pushed into the stack. After that, until my stack is empty, this entire process is done. Whatever pushed one immediately popped recent one. Then if the current vertex is not visited, definitely not visited. After popping only it is marked. After popping, it is marked as visited is true. And then who are adjacents of this current vertex, they are not visited means immediately push them. Once you push them, only vertically the recent one only popped, and the recent one again depth is there, it is going towards depth. So finally the visited one will become, it is all the things are true. That true it is printing. This is what the true. Now my question is, for example, your graph is having collection of components, something like this: A, B, C. This is one component. D and E is another components. Now my question is, what is the visited matrix status? Can anybody tell that? If you start, the starting vertex is this, using DFS or BFS, anything. I don't say BFS or DFS. Starting vertex of this entire one is a single graph. We consider this a single graph. If I start that BFS traversal or DFS from A, can you say what is the visited matrix status? Sorry, visited dictionary status?
True for ABC and false for D.
So what it contains is true for A. What about B? What about B?
True.
True. What
True.
about C?
True.
What about C?
True.
True. What about D? Because they are not connected. They are not adjacent, so that they still remain false. So what exactly is, if a graph is there, you have started from a starting vertex, either BFS or DFS, some of them visited false means definitely there is a disconnected components are there in the graph. There are different groups are there. So that you can identify, of course. So some next problem is there. In the next problem, you can see that. Yeah, here it is recursive approach. Recursive approach, again, they are telling, initialization function they have written. All visited, they are make it as a false. Parent information, they are updating it is -1. This is only one time call. But DFS list, they are calling repeatedly. See what way they are calling is, recursively, they are calling by sending visited and adjacency list as a parameter, parent information as a parameter, adjacency vertex as a parameter. So that first A is traversed, then A adjacent B and C is there. In that B, they are picking up. From the B, they are going. For example, if it is A and B and C and D is there, E is there, maybe you have a graph like this. You're starting of the DFS, it will start with A. After that, it goes to the next level, that is DFS of this. Immediately, DFS of this B you are going. After going, again the recursion will call to here. So again DFS of D. The DFS of D is calling DFS of E. After DS of E is calling, E is having one adjacent. So that this is what adjacent. Every time the current vertex adjacent you are calling recursion. So that DFS of C. So that the traversal, it's coming in a recursive cut-off approach. Every time, so we are sending that the vertex which you want to traverse is that adjacent vertex. When you call the adjacent vertex, you are going towards a depth. That to first adjacent. First adjacent means what? Who is at top of the in the entire adjacent list. Maybe 3 or 4 adjacents are there, but top adjacent only we are going towards depth. So this is recursion with initialization. Sorry. Yeah. So recursion with global variables also they have given. This is to shorthand your code. Nothing else here. But most of the things are same, but only shorthand your code. They don't want to do initialization. Here it is. Okay. It's in the matrix. Yeah, here it is. Global variables. So if you want to use a global variable, the parameters can be reduced. Every time this visited and parent information, I need not send it. If you could see that earlier one, you need to send it these two also as a parameter. These two parameters you can avoid by using a global variables. These global variables are accessible for anywhere. So every time you can update anywhere. So every time, this is for initialization as usual. This recursive approach is taking only 2 parameters, that is adjacency list and adjacency vertex, which you want to traverse in a depth. And now this is using adjacency matrix. This is another figure outing of that particular one using adjacency matrix. This could be another approach, but it is complexity is somewhat you can say that it is not efficient one. Here also global kind of declaration they are using. But here the interesting thing, as earlier I said, components you can have in a disconnected graph. Just like a larger graph is there, it might have inside subgraphs or subcomponents. Now the thing is how to find connected components using BFS. So the interesting graph was given. See, look at here. How many components are there in this graph? Can you identify? How many components are there? How many components are there? Hello.
Two.
Hello. Two components, correct. So these are all component number 0. Maybe 1 or 0. I can say anything. Maybe 0 component or 1 component. Oh, sorry. This is belongs to the first component. Maybe it is 1 and it is 2. So here 2 components are involved. So how to identify them? Total components we want to find out it. So this is an interesting approach. See, look at here. Here, of course, BFS only they are using. I want to make it zoom. Yeah, the approach you want to make it zoom. Yeah, here it is. See, create a queue and erase a widget. Widgeted is keeping the track of that whether the vertices are widgeted or not. Basically, they are all false. Initialize the dictionary of the component is -1 because basically everyone they belongs to -1 only. Because which component it belongs means I don't know. So that -1. So this is a -1. All of them are -1 because basically nobody knows that which component it belongs to. So the next one is, can you mute somebody? Yeah. So basically initially it doesn't know that which component it belongs to. So that all of them it becomes it is -1. So after -1, we try to use a BFS traversal. Whatever widgeted things are there, widgeted components are widgeted vertices are there, that vertices we want to update a component dictionary. The component dictionary belongs to the -1 will become that 1. Now here repeat this process until all of the things are widgeted. How would I know that all of the things are widgeted? Is the simple implementation what they did is they tried to start that widgeting the smallest vertex in this component. What is the smallest vertex in this component? Can you tell me in this one? What is the smallest vertex?
3.
What is the smallest? 3. So they started from here first. After this is over, next component, what is the smallest one? In the unvigneted list, what is the smallest one?
0.
So that next it will start it from here. So this is going to be next start. So that counting they try to check it until all of them are. So look at here. The queue is as it is. They don't change of it. Here, widgeted status is all of them are false. And here, you can check it here. The queue it is created. Starting vertex is true. Here it is, adding that starting vertex into the queue. Until my queue is empty, we are dequeuing and we are doing it as adjacency vertex is whatever adjacency is becoming is true, and immediately that is added into the queue. Finally, widgeted matrix. Now this is a BFS one. This BFS one, it tries to visit any starting vertex. As I said, first we try to start it from here, then we try to start it from here. So that minimum checking we try to use it. To that, they are using this component. You can look at here. They are taking the components list as a parameter. Basically, component dictionary they are creating. Which component it belongs means all of them belongs to -1. Initially, all of them -1, -1, -1, -1, -1, -1, -1. Of course, this one also -1 because nobody knows that which component they belongs to. So now, so here, interesting thing happens. Component ID is updated. Current seen status, whether it is seen or not seen. So what is the seen count is there? That counting, how many of them are seen? Seen means widgeted. So total, how many vertices are there in this? Total 10. Is it right? 10 vertices are there, 0 to 9. Is it right? Hello.
Yes.
So all of them are visited means my scene count will become 10. Is it right? Is it right? Hello? Hello? Somebody has to respond because I don't have that any kind of motivation.
Sir, once again tell me, sir, how it is all are visited?
By default, all of them are -1 status. Is it right?
Yes, sir. Yes,
Because
sir. That is okay.
They don't know that which component they belongs to. Is it right?
Yes, sir.
Now, component ID and scene of the 0th vertex is seen, because basically we try to start it from 0th vertex. Sorry, I'm sorry. Hello. Yeah.
Yes, sir.
Component ID and scene initializing representing with 0, 0. Okay. Okay.
Okay, sir.
Now we try to repeat this outer for loop until all of the maximum keys of adjacency list. How many maximum keys are there in this? 9. Is it right? Hello?
Outer loop means
see here the component. See, outer loop means this one, this while loop. This while loop is repeated until my scene value reach to maximum of the adjacency list keys. What is the maximum adjacency list? 9.
9, sir.
Because all of them are visited until this the loop is repeated. Is it right?
Yes, sir. Yes, sir.
Now we try to pick out minimum. I said minimum of the adjacency keys, and if the component ID of I is -1. -1 means what? Not visited. Clear? Hello?
Yes, sir. Yes, sir.
So that starting vertex we are picking out. One of the starting vertex we are picking out means, so maybe starting vertex minimum you are getting that 3 maybe you started from 3 because
yes,
out
sir.
of this particular one.
Yes, sir. Yes,
so
sir.
once we got it from the 3, that could be considered as a starting vertex. So this 3 is starting vertex. Using starting vertex, BFS traversal will be done. Clear? Hello? Using starting vertex, BFS traversal will be done. Once BFS traversal will be done means what happens that this component,
Sir, my only request is, sir, it is minimum I, it is mentioned, no, sir. Then it should be 0, no, sir. Why 3?
No, wait.
It should start at 0.
Wait. Look at here. What they have done is they are calling components list of A list. A list means this adjacency list they are calling. Once it went for the adjacency list,
Yes.
so what is the initial ID they have taken?
0, sir. 0.
Okay, 0 they have taken. Component of 0 is -1. Adjacency list of keys they are taking. Here, keys in that each key you are getting. Is it right?
Yes, sir. Yes, sir. Yes, sir.
In that each key you are getting means minimum means you are right. 0 you are getting.
Yes, sir.
Correct. So here not 3, 0. Clear? So using 0 BFS traversal it works. Clear?
Yes, sir.
Hello. So
yes,
once BFS traversal it works, what happens that due to the BFS traversal, this visited will become true. This visited will become true. This visited will become true. Is it right?
Yes, sir. Yes, sir.
Because BFS will start it from here. Clear?
Yes, sir.
Now, but remaining this component are false. Now, so this BFS visited traversal is updated. Now, what happens? Assign the component ID value to each reachable vertex from starting vertex to the increment of the scene value. So whatever the visited keys are there, the visited keys means what? 0, 1, 2 is we are getting. That keys you are getting. Is it right? Because 3 only visited, no? Clear? Now,
sir?
these 3 are visited or not? These
yes,
3 are
3.
So
0, 1, 2.
These 3 are visited. They are visited is true. Then what happens? Scene will become increment to 1. What is my scene value? 0 will become 1. 1 will become 2. 2 will become 3. How many vertices are seen now?
3. 3
vertices are over. So scene count will become 3. So 3 of them are over. Clear?
Yes, sir.
Now Again, this while loop it checks. Sorry, component ID is increased to.
Now scene is 4.
Wait. Component ID, all of them belongs to component ID 0, because whatever widgeted, these are all belongs to component ID 0. Is it right?
Yes, sir.
Their
Yes, sir.
widgeted is true, right?
Yes, sir.
Over. That's clear.
Scene
Now,
is 3, sir.
Scene is 3, correct. The
Three
scene is incremented to 3.
3,
Okay.
sir.
3.
3 plus 1, 4.
Wait, no. Scene is started from 0, 0 plus 1, 2 and 3. After 3, it is stopped. Clear?
Yes, sir.
Okay. Now, does my 3, is it less than 9?
Yes, sir.
Again, this loop is repeated. So while loop, now what it will do, whichever components are -1 is there, in that minimum 1 is selected. So now this component is over. Is it over? This is over, no?
Yes, sir.
Now these are -1. Is it right?
Yes, sir.
Out of this -1, what is the minimum one?
Minimum one is 3.
Correct. Now 3 is used as a starting vertex and it will do another BFS traversal. Here.
Yes, sir.
Now, whenever BFS traversal it is doing means all widgeted will become true. The widgeted keys you are getting, their scene value is updated to scene +1 and component ID is updated with another component ID, so that all will become one component. Component ID. These are all zeros, already zeros there. Okay. These are all 1. Is it right?
Yes, sir.
So that is 1. These are all 1. So that is done. Finally, what happens that, so my particular component, scene value will become 9. Is it right?
Yes, sir.
Does my 9 less than 9? No. This loop is stopped. Is it right?
Yes, sir.
Now what happens, the component dictionary we are returning. So look at my component dictionary. 0th vertex, first vertex, second vertex belongs to component number 0. Is it right?
Yes, sir.
But 3rd to 9, these are all belongs to component number 1. Is it clear?
Second value is component, sir.
Correct. This is that vertex, which component it belongs to. Is it clear?
Yes, sir.
Okay. So this is another application of this particular BFS which you are using. And another interesting application of the DFS is pre and post numbering. So let me mute for all of them, because all these are theoretical concepts but interesting applications which make you that better. See, look at here, pre and post numbering. See, I want to go with another example, pre and post numbering using DFS. Directly, I don't want to walk through the code or algorithm. So let me go with a typical kind of graph. Hope my screen is visible. You have pre and post numbering. Pre and post numbering. What really happening is pre and post numbering. So I'm taking a graph, maybe some kind of typical graph, D and E. I'm trying to do with some F also. A is there, then B is connected to D and E, and D to E also there, and now C to F is there. That's what I want to use it. So I want to use that DFS. So pre and post numbering using one of the application of the DFSs, pre and post numbering. See, for every particular connected graph, there is a traversal tree generated. If you can do that, a BFS algorithm is applied on this graph. This is a graph G. Graph G. If DFS is applied on this graph, what is my tree generated? Can anybody tell that? A tree is generated. What is my tree generated? Can anybody tell that? What is my tree? How it looks like? if DFS is applied. If DFS is applied, what way it works?
A, B.
A, B. After the D, after the D,
D, D.
after the D. Okay. Then it is no more further depth is there. So next we are going for the C.
Yes.
Then it's going for the F.
This
This
is
is what this is that DFS traversal tree traversal using DFS.
So that would be K, sir.
Now, what is the case? I'm not
Okay,
asking.
okay, sir. Actually, it looks like K and the symbol E you have written. No?
Okay, okay. So it's a C. Okay.
The E
D.
is
E is okay. Okay.
no, sir. On the right graph.
This
in
is
the
E
black.
only, no? Okay, this is
It
E.
looks like K.
Oh, sorry. This is E. Okay. Yeah.
Sir, what does it mean pre-post, sir?
Wait. I'll tell you what is that pre-post. That's what I'm walking through. Just wait. Huh? Yes. This is my E. Now the thing is, so pre and post numbering. So now you found it. The particular tree traversal is there. The tree traversal forward edges are there. So you look at this. They're all forward edges. If you could see that, this is a forward edge. This is a forward edge. This is a forward edge. Am I right? This is a one forward edge. Using that DFS, it was created. Now the thing is, there are three different edges are there. So I'll tell you what is the three different edges. Generally, tree edges are, it looks like this. These edges are called as tree edges or forward edges. Generally, what happens, you know, there are forward or tree edges, tree edges, and there is back edges are the back edges or backward edges. I'll tell you what is that one, don't worry. There is some cross edges also there. So these are three different kind of edges. We can identify them using pre and post numbering. You can find out that whether the cycle is existed or not, you can easily find out it. So let's do that. Maybe, you know, pre and post numbering. So generally pre and post numbering, we can say that, let you consider, because I don't want to walk through the code. So you can consider it is a tuple value. Maybe pre and post, it looks like this, pre and post, two values. So initially, maybe they'll start with pre and post. Let's start that pre is here. We don't worry about the post now. So it is 0. Let's start with that forward edge. A to B we are going means you are going in this direction. That means A to B. Immediately pre will become increment by 1. So that this 0 will become 1. Am I right? You are going that DFS traversal from A to B means you are going that the pre value is incremented to 0 to 1. Is it clear? Is it clear?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Now, from the B to D, you are traversing forward. So that another forward edge is formed. So this 1 will become 2. Is it right?
Yes, sir.
From the 2, from the D, you are going another forward edge. This 2 will become 3.
Yes, sir.
Is it right?
Yes, sir.
After going for this 3, again further there is no depth is available. Is the depth is available? No depth.
No, sir.
Whatever pre value is there, that plus 1 is a 4 value. So this pre value is currently it is 3. That plus 1. What is that 3 plus 1?
4.
So that current backward edge value is currently it's a 4. It is coming reverse back because backtracking will be executed. Is it right? Because
Yes.
it's a recursive structure, no? It's a recursive structure.
Okay, sir.
Clear? Once it is recursive structure, the backward incrementing is going on. Pre plus 1 is the current post. This post is started incrementing. When it is incrementing to here, this 4 plus 1, what happens? It is 5. Is it right?
Yes, sir.
This 5 again backward, back traverse. So this one will become 6. Is it right?
Sir, but it can go from E to B also, no, sir?
No, no, no. This edge is not used in forward. How it can go in that way?
Okay.
Because whatever recursive one we call it, that way only we are doing a backtrack. Clear?
Okay.
Now, this is over. But whenever it is coming back from here to here, still that backtracking is not over. Still there is a depth is available from the A. Is it right?
Yes, sir.
So what happens, you know, whatever the post value already available, that plus 1 is the pre-value. So what happens, you know, the 6 is there. This 6 will become the 7th vertex. Is it right? Already this is a post value. What is this value? Post. This post plus 1 is the pre-value here. So this is going to be 7.
So why, sir? A should become
No. Still
0,
A
7, no?
is not end of backtracking. A is a not final call. See, where it is started, there it is ended. Is that recursion is ended at A? No. Still there is a recursion calling. Is it right? It is not ended. Still there is a depth is there.
Sir, we are not saying ended, sir. Even
No,
B...
not ended. Not ended. Still there is a depth. Is it visited or vertices is visited or not?
Not at visited.
Not at. So there is another tracking is there. See, look at here. These are two different paths.
Yes, sir.
So now this 6 1 plus 1, it is 7. Again from here, I'm talking about here. Yeah.
7 is post or pre, sir?
Previous post plus 1. It's a pre only. Previous post plus 1. This is pre only. But previous post is there, no, that plus 1.
Yes.
Now, again forward. Once it is going forward, it's become 8.
Yes, sir.
Is it right? So
yes,
after going 8, there is no further. Whatever pre is there, that plus 1. So earlier we done it. So it will become 9. Now backtracking will be executed.
Yes.
It is coming here. So this one will become 10.
10.
Once it is coming out and the last backtracking call here is 10.
Not 11.
sorry. 11. I'm sorry. 11. Now you see that. The thing is, here, let you consider this is U and this is V. Can you say that vertex U and vertex V? Is it right? Is it right?
Yes, sir.
U to V we are going.
Yes, sir.
Either this you can say U to V, you can say. Now, the forward edges is, the condition is the pre of U and post of V, post of U, both contains pre of V, this is a set, both contains pre of V and post of V. See, I'll tell you that what exactly this. See, look at here. For example, you consider this is a U, this is a V. Can you tell me pre of U and post of U? This is 0 and 11. Is it right? This is 0 and 11 or not? This is 0. This is 11. Is it right?
Yes.
Yes, sir. Yes, sir.
Now, the pre of V and post of V. What is this 1 and 6? This is 1 and 6. Is it right?
Yes, sir. Yes.
So these pre values are inside range of this particular, the V values are inside range of U values. Did you understand? See,
No, sir.
1 and 6 is in between 0 to 11. Is it right?
Yes, sir.
So that indicates that it is a forward edge. It's a forward edge. Now you can say that back edge. If it is back edge, it is reverse. What exactly reverse is? The pre of, the pre of V, I'm sorry, maybe I'll do that some kind of story. Yeah. So here I'll use a different color. The pre of V and pre of u, they contains inner values of pre of u and post of u. This is v, this is u. Now let's see the package. See, I said it is v and u. For example, I can say this is v, this is u. Is it okay? Is it okay? Hello?
No, sir,
Yes.
we are checking, sir.
Yeah, package I'm talking. The package is the pre of v and post of v. So the pre of v and post of v is there. Okay. This contains that pre of u and post of u. So the post of u and pre of u, you can say the package. So they are inside of it. See, you can see this package is there. This package is in the range of 1 and 6. Is it right?
Yes, sir.
Now, interesting thing is there is a cross edge is there. For example, by mistake, we have a graph connection like this. Maybe your graph is connected like this. Like this.
Sir,
Hmm.
so I have a doubt in package again, sir. Can you please explain it?
Yeah, sure. Just a minute. Yeah. So the package is the pre-value of v and I'm sorry, maybe this is v, okay, but it's okay. These are inside range of that. Okay, sorry, I'm sorry. Actually, when I'm doing a backtracking, I should use this should be u. Is it right? This should be u. Is it right? Because backtracking, no? Package means this is u and this is v. Is it right? Hello?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Then pre-value of v and post value of v, this is post value of v. These things contains that pre-value of u and post value of u. So that 1 and 6 between, there is a range of value of 2 and 5. Is it right?
Yes, sir.
So that is what reverse backtracking. So that's called backage.
Sir, you can say forward edge on the other side is a backward edge.
Correct. Now there is a cross edge is there. Sometimes there might be a graph. Your graph, it might have edge. For example, like this. If you have an edge like this, what happens? These two values are completely disjoint. You can check it. For example, this is u, this is v. I'm using a blue color. You can check it. The particular pre-value of u and post value of u, okay, this is completely disjoint. There is no matching. There is no in the range. Complete disjoint of pre-value of v and post value of v. Let you take it. What is my this u value? 3 and 4. Is it right? Is it right?
Yes, sir. Yes, sir.
What is my this 7 and 10? Is it right?
Yes, sir.
7 and 10, no?
Yes, sir.
So that particular 3 and 4 and 7 and 10, you can check it. This 3 and 4 is not in the range of 7 and 10. 3 is below the 7. Is it right?
Yes, sir.
4 is also below the 7.
Yes, sir.
Because it's a cross edge.
Sir?
Tell me.
There is no edge at all there.
No. Assume that there is edge. Example, I'm telling. How can you find out that cross edge is? If the values are disjoint, values are there. Sometimes the graph, it looks like this. Maybe before DFS, your graph, it is having, there might be edge, for example. Then what happens that, is it used in the DFS? It might be used in DFS, no, because the depth will go to the E. From the E to C, you are going or not? Are you going? Are you going or not?
Yes, sir.
Yes,
You
sir. We are going.
Might go, no? E to E, because A to B you are going. B to D you came, D to E you came, E to C also you can go, no problem, because the depth now clear. Still backtracking.
And we will go to C to F also, no?
Then it, after going for C, then it comes to the next depth. What is the next depth is C to F. So then this particular path is not existed. This is not existed. Is it right? Is it right or wrong?
The particular path will exist, sir, but it will not be counted, sir.
Yeah, path is exist, but DFS is constructed in this way. What way the DFS is constructed? A, B, D, E. After E, what happens that it goes to C.
C and F.
Yes, C it goes, then it goes to F over, because already A is done. Clear? Hello?
Yes, sir. Yes, sir.
So that case also there. Then how can you find out the disjoint vertices is, this is a disjoint because they are not in the range. They are in 3 and 4 is not in the range of 7 and 10. Either they might be prior values or these might be post values. Higher values. These values are completely below the 7. These values are completely above the 4. So that kind of edges are there. So you can see that actually.
Sir, one doubt. Please show the diagram, sir.
Yes,
so,
yes.
BE. BE is nowhere given forward or backward.
No, because
it seems that the range is falling inside that B. So shall we say it's a forward?
Backward, no?
Yes, you can. For example, if E to B is there, E to B, when it will be there, when only B is not visited, then only it's visited. No, clear. It's already visited. How it can go from E to B? Is it right?
But this edge is there, no, sir. What is the
edge is there? But we don't use the
edge
BFS.
name, sir?
We don't use the BFS. This is BFS. Sorry, DFS traversal. This is a graph. This is a DFS. DFS traversal edges only considered in pre and post numbering. Clear?
Yes, sir.
Graph.
Sir, but sir, but while detecting whether an edge is forward and backward, we go back to the original graph, no? We do not.
No. This I supposed to use this graph only, but actually to understand it only. But you can check the path. I did not use this path. Is it right?
Yes, sir. Yes.
Maybe I supposed to use this graph, but unfortunately I used that. That's it. Okay. Okay.
So, sir, in this original graphs, this path from E to B becomes the backward edge?
No. It cannot be considered because DFS will not be used this edge for traversing. So that's what, see, look at here. Please consider this one. Actually, unfortunately, I used this, but actually I supposed to use this one. Here.
Sir, okay, sir. Then what is the edge? Name of the edge B?
This edge is a graph edge, but it's not a DFS edge.
Okay.
It's available in the graph, but it is not there in the DFS traversal. Clear? Yeah. All edges available in the graph is not included in DFS traversal because it wants to just create a tree. Clear?
Okay, sir. Okay,
tree is not a acyclic graph. Is it right?
Yes, sir.
Yeah.
Okay, so so then whenever we want to identify forward, backward, and cross edges, we just need to look this DFS tree.
Correct.
Else.
Correct.
Okay.
Sorry, actually, I supposed to use that one. Yeah, here it is. Yeah, here it is pre and post numbering. They try to use this graph. Actually, maybe this is so complex one, but it's okay. You just mute everybody. You can mute. Yeah. See, look at here. I'm walking through the code. Yeah. See, look at here. There is DFS only they are using essentialist. Global variables they have taken. Here pre and post numbering they have taken as a dictionaries, 2 empty dictionaries. Here you can check it. Initially the count is started, whatever the count value which you sent it. Basically the count they sent it with 0 value. You can see that one. That is the second parameter of it, count. So that count is assigned with 0 as I shown you in the diagram. So the count, of course, it is started with 0. Similar lines they have initialized with pre-count is 0. Then count is incremented to 1. Whenever that next vertex you are trying to traverse it, the count is increased. From the current vertex, the starting vertex, all adjacents you are picking up, whichever not visited, that not visited one we are using for DFS traversal. So once DFS traversal of the pre and post list they have called it, recursive approach is used. Whenever recursive approach is used, the next count we are getting. So that what happens, you know, it going for that pre count is used for the next count plus 1, next count plus 1, next count plus 1. But once this recursion is over, this particular one is updated. Post value is updated with the previous count. Hope you got it. Is it right? This recursion is ended means what? It is going back. When it is going back, earlier pre is there, that is used for the post. Is it right? This one?
Yes, sir.
And the incrementing of count is there, because after that post count is updated, next you need to update that count plus 1, because you're going back, the post is updated. Again, the counting sequence is as usual. So that counting sequence is a final counting sequence. We are trying to return it. Whatever the counting sequence we got it, that they try to use it. Yeah, here it is. You can check it here. See here, you can see that some of them are visited is true, some of them is false, because you can see that it is a somewhat typical graph. They have used it. They're supposed to start it from 0th vertex. From the 0, whatever possible vertices are there, they are marked as visited. They try to make it true, so that these are all true. These are all true, but these are all false. Interesting thing is, so that was happened by this one. You can check this one. 0 is visited, 1 is visited, 4 is visited, 8 is visited, 9 is visited, because they're disconnected components. Now they try to bring the pre-numbering. The pre-numbering, if you could see that, whichever visited only the pre-numbering is updated. So you can see that from the 0, if they have started from the 0, it is a directed graph. 0 to 1 it went. So maybe if you could see that pre-numbering, we start the pre-numbering is here. What is the next pre-numbering? It will come to 1. Is it right? Is it right?
Yes, sir.
Yes, sir.
Now,
Yes.
after this count, it will become 2. Is it right?
Yes, sir.
Because no further depth, no. Is it right?
Post, sir. That is.
Post
is
value
post.
is a pre 1 plus 1.
Yes.
Here. Now it is coming back to the back edge. When it is coming back to the back edge, the earlier value plus 1, is it done? No, because still that adjacents are pending. Clear? Hello?
Yes, sir. Yes, sir. Yes, sir.
So when adjacents are pending, so what will be the value of here? So you can
1.
check it. So
1.
this
3.
3.
No, 3. The pre-numbering of this one is 3. From this 3, either it can go, let us assume that it is going for 8 because chronological order. From the 3, it is going for the 4. Clear? From the 4, it is going to the 5. Once 5 is over, no further depth. It will become 6. Clear?
Yes, sir. Yes, sir.
So
6.
once it is going for the 6, backtracking is done. Once backtracking, this 4, it is 6 plus 1, it is 7. Then backtracking is done. Then the 7 plus 1 is 8. Then backtracking is done. So when the backtracking is done, this is 9. So remember, this is the pre and post value for the each vertex. Let me screenshot it, whether my thing is right or wrong, because once I'll close it. But these things are disconnected. We don't worry about that. So I'll stop it. My particular pre and post value, my screenshot, whatever it's there, it is matching or not, we'll check it. Maybe just now I've done a screenshot. Yeah. So to understand that
Sorry.
it is my, yeah, here it is, list. The recent one, here is my this one. Here is my list. Whatever pre and post I created. My screenshot is this. Okay. Say, look at here. My values are here. My this numbering is here. Yes. Maybe still it requires some more time, some more dragging. Here it is. Still, I want to reduce this. Yeah, here it is. Okay. Yeah. So let me do that. The 0th one is having pre-numbering is 0, post-numbering is 9. Is it right? Is it right?
Yes, sir.
One is having 1 and 2. So that's done. So now that 3 and 2 is not reachable, that's okay. But 4 is having that 3 and 8. Okay, 3 and 8. So similar lines. So the 5 is not reachable, 6 is not reachable, 9 is reachable, 5 and 6 is there, 8 is reachable, 4 and 7 is there. So it is pretty much that 4 and 7. Yeah, over. So simply we try to find out the pre. See, but here there is a running nodes is there. You can see that. Remember, the edge UV is a tree edge or forward edge. If interval value, the value of that pre of u and post of u contains that inner range of pre of v and this, because these values of pre of v and post of v, they are inside range of pre of u and post of u. That is called forward edge or tree edge. The backward edge is there. So they are in reverse. These are higher. The v pre value and post value is higher. And u pre and post values are smaller values. And there is disjoint values whenever cross edges. We don't know, cross edges are some different edges are there, but they are not included in your DFS traversal. If you try to compare, there might be actual joint is there, but it not be considered inside your DFS traversal. If it is considered, it is completely a cross edge. So that's what cross edge we can find out. So this is one interesting application where that the DFS traversal we try to use it. And last easy concept and acyclic graph algorithms. See, it is directed acyclic graph. Remember, a directed acyclic graph is a directed graph. This is another application and important algorithm where frequently asked in your PYQs and all. So any directed graph, and if it should be that acyclic graph, then you are calling that graph is called as DAG. It's a directed and no cycle exists. Remember, that's mandate. If that is kind of graph is there, that kind of graph you can do that. Some algorithms called topological sorting. Even you can take the example of your IITM BS degree. So you required that 6 or 7 or 8 terms to complete your all courses. Some courses have prerequisite courses. If you want to do that MAD1 course, you're supposed to finish that at least co-requisite or prerequisite of DBMS course. So that kind of pre-dependency is there. Some of them are independent, some of them are pre-requirement is there. So such kind of application, see, look at here, there is a topological sorting. So what is the topological sorting is, we try to identify that what is the maximum minimum number of terms required to complete that entire IITM BS degree. If you are simply at a stretch, you are trying to finish that, fully focus on no other parallel course you are doing, how many years it requires, something like that. Similar way, you want to find out that, so number of dependencies you require based on consideration of it. So here the topological sorting is very simple. So what the topological sorting is, here, as I said, it is a directed graph. Whenever directed graph is there, let's recollect that in degree of the graphs. So the in degree of the graphs means maybe, dependency it represents. For example, if you could see that 0, 1, 2. It's a acyclic graph. Is there any cycle existed? No cycle. Is it right? Is there cycle existed or not?
No, no cycle.
No cycle. Fine. Now, what is the in degree of this 2? Vertex 2?
2.
Correct. In degree of this one is 2. What is the in degree of this 0?
0.
Fine. In degree of this one is 0 because there is no incoming. What is the in degree of this?
1.
So what I can say is, to do this course number 2, you must finish that earlier 2 courses. This 0th course you need to finish, first course you need to finish. Then only you can do the second course. Am I right or wrong?
Yes, sir.
So that dependency.
No, sir. No, sir. You are not right, sir.
Why?
0 course, if you finish, you can do second.
How? How? If you finish
directly,
the 0
direct
course,
arrow is there also.
No. Wait. After doing not arrow, the in degree of this one, it represents that second course, it requires that two requisites has to be done.
It's true, sir. But there is an edge.
No, edge is representing in degree. What is that in degree meaning? Dependency. Is it right?
Okay.
2 is dependent. Course number 2 is dependent on course number 1 and course number 0. Clear? Yeah. Now you look at here. How to do this topological sorting is, because I don't want to go for this theoretical approach. Let's consider this graph only. I'm taking this graph only. How really the topological sorting works. Look at. Just I want to do that. Yeah, as small as such. Here it is. Now still not simple. Yeah. Now my graph is okay. Is it okay? Now, first we try to compute that all of the in degrees. What is the in degree of this 0th vertex? Can anybody tell that?
0.
Correct. What is the in degree of this 2?
2.
Correct. What is the in degree of this 7?
4.
Correct. What is the in degree of this 0?
0.
This one?
1.
Still small is required because some more vertex is there here. It's more typical. Yeah. Okay. Maybe I'll erase this. Maybe it is 6 is there here. I want to use that. This is in degree 0. This in degree is 2. This in degree is 4. This in degree is 0. This in degree is 1. This in degree is 2. This in degree is 1. This in degree also 1. Of course, 6 is there. That's in degree also 1. Is it right? Hello?
Yes, sir.
First, we are starting that topological sorting from any vertex which is having in degree 0. Either you can start this course or this course. Is it right? Because they are not dependent on anybody. Is it right?
Yes, sir.
Yes, sir.
Now, once you visited is true, immediately what I do is this edge or dependency I can remove. This edge or dependency I can remove. If you are considering this is your starting vertex. Once these edges are removed, what is the in degree will become here? It will become 1. Is it right?
Yes.
Yes, sir.
What is the in degree will become here? 0.
0.
Now, so after that I can complete this one also because it is not dependent on anyone. This one also I can finish it so that visited is true. Once it is true, this in degree, edge, outgoing edge will go off. This outgoing edge will go off. Once it will go off, so what it will become is, it will become 3, it will become 0.
Sir, one doubt, sir. Instead of 1, I can take 3 also, sir.
How can you take the 3? What is in degree? Yeah,
0.
you can take. You can take it. Yes. Instead of 1, any vertex which is having 0 degree, you can. No problem. Okay. Okay, fine. Now,
Okay, sir. Okay, sir.
yeah, now 0 degree, this one is visited. This one is visited. You can choose either vertex 2 or vertex 3, your choice. As per your wish, I want to go for vertex 3. So this is visited true. Once this is visited true, that outgoing edges are removed. Once outgoing edges, it is visited means no dependency. So that what happens, due to this edge is removed, this one will become 2. Due to this edge is removed, this one will become 1. So after that, it is keep going. Now, any 0th vertex is there. This is visited. Now this is visited. Once this is done, this vertex is removed. So its integrity will become 0. Yeah. So still 4 cannot be, 4 also can be done because it is done, no? It is 0. So 4 also it becomes 0 because 0th vertex is visited true means. Now 0 vertices, 4 is there, 5 is there. Yeah. 6 is there. Sorry, 6 is 1. Still incoming vertex is there. Either you can choose 4 or 5, whatever choice is yours. Maybe I've chosen 5. This is visited true. Once visited true, this vertex is removed. Once this is done, it will become 0. Now you have a choice of 4 and 6. You can choose any one. I might choose in this one. This one will go off. This one will become 1. After the 6 is done as true, this one will become edge is closed. So this one will become 0. Now the thing is, to complete this, all of this topological sorting, I'm sorry, I'll make it zoom. Yeah. Okay. So let's do that graph drawing. Is switch it off. Still, I want to reduce zoom. Yeah. Clear. So now let's understand this, what kind of implementation they have done the topological sorting. Every time they try to choose that 0 vertex in degree, based on it only they try to process. And one more thing, it is acyclic graph. Make sure that if you want to do the DAG, it must be this one. See that where you try to use this one is construction of a project, cooking recipe. You want to make it. Cooking recipe means first we have to put the bowl, then you have to add some oil when you want to cook a particular dish. So that is a sequence of it. So prerequisite between courses, that's what best example. You can see that. Compute all the integrity of the graph. Now NQ the particular vertices which are in degree 0. Which of them in degree 0 is there? That we are picking off it. We are trying to add them into the queue. While queue is not empty, we are removing one particular node from the front of the queue and add it into the sorter list. That means sorter list means topological sorter. So for each particular DQ node neighbors, decrement in degree -1. -1 you are doing means that edge is removed. So keep doing it. If any DQ node neighbors have that 0, again NQ them into the queue. Repeat this particular one. So that's how the process. Implementation code is this. So the queue help they are taking. Topological sorting, you can take a look. In degree, there is a dictionary they are taking. Topological sorting is order of traversing of edges. 0 degree queue they are creating. Then they are trying to update that in degrees. Wherever that in degree of this particular U is there, that's updated. Now, whatever that in degrees we want to count it. If there is edge from U to V is there, immediately we are increasing. If there is an edge, increment that in degree. If there is no edge, don't increment. U to V, there is edge means immediately we are updating that in degree of V. U is a source, U is a source, V is a destination. If there is edge between these two, the in degree of V is updated by +1. Already 0 is there, +1. If another edge is connected, it will become +2. Another 1 is added, so it will become 2. So that in degree is updated here. This exclusively for updating in degrees. Once done, now find the vertices which are having 0 in degree. Whatever in degree 0 are there, they are directly added into the 0 degree queue, which is empty queue. We are trying to add them. Until my queue is empty, we are trying to repeat it. We try to extract that each particular element from the first in, first out format. Now the topological, whichever current vertex we are getting from the queue, that means 0th vertex, 0 in degree vertex. That 0 in degree vertex is added into topological. So first 0 is visited, then 1 is visited, then 3 is visited. Whatever visiting sequence is there, that visiting sequence you are getting into here. After getting in visited sequence, we try to do the subtraction, because once edge is gone, in degree is decreased by 1, -1. So keep doing this. The order of traversal is this: first 0, then 1, because both of them in degrees are 0, then third vertex, then 4, then 2, because 2 is traversed after 3 and 4. If you go back to that, maybe 2 is having incoming edges from 3. I'm not sure. Yes, 2 is having incoming edges from 0 and 1, so that's processed. Anyway, 3 is processed. After 3 is processed, they try to process 4. No problem. 4 can be, because 0 incoming is gone, 4 will become this one. Clear? So that's what you got, this particular topological 0, 1, 3, 4, 2, 6, 5, 7. So, but make sure cycle should not exist. And using adjacency matrix, we don't consider, because it is, another longest implementation, or you can say that lengthy implementation. Now, the lengths also you can calculate. As I said, how many number of terms to finish that entire BS course, all prerequisites and all without prerequisites, is that you want to find out it. So that is also you can do it. This is what one particular approach. See, this one also you can do that longest path. Maybe I don't want to use this graph. I'll take some other graph. See, I'm drawing a particular graph. Maybe it is a typical one, so that you will understand better. You have A to B. Let you consider these are courses. You can consider courses. C, it's one course. D also one course. So what exactly is BCD courses required prerequisite of A? Am I right? Am I right?
Yes, sir.
Now, E is a one course. F is a one course. It is having only one particular prerequisite. F is having two prerequisites. Let's consider. And then we are taking some I and J. Maybe it is a typical or complex graph. So that to make it better understanding, I'm using it. So one more G also I'm taking. So this is also having dependency, and this is having dependency of it. Of course, H is not connected to F or anything. So now this is connected to J. There is no cycle existed. That you must care about it. And after the J, there might be another one is K. You can have this one. I hope this is pretty much. Yeah, this dependency also I want to give it. Now, this longest path, what it will find out is how much time, how much the number of years to finish up that courses from A to K. The first course from A, and the last course to K. So I want to find out it. So I can do it. So I think in the first year, you can finish up this one. Is it right? Is it right? Because this is 0 in degree. In degree 0, no? Clear?
Yes.
So whenever these in degrees are 1, it's okay. Once this is done, this in degrees will become 0. Is it right?
Yes.
Yes, sir.
So I want to use it. First year I can finish up this one, or first term. In the second term, I can finish up this one, so that This one I can finish, this can I can finish, this can I can finish. Is it right?
Yes, sir.
Yes.
Because in degrees are 0. So once this is done, this in degrees will become whatever the in degrees of this one will go off. This in degree will become 0. This 2 also will become 0. So once this is done, I can do during the third term, I can do that courses of E and F. Is it right?
Yes, sir.
Yes.
Cool. So now H is anyway in degree by itself, it's a 0. Clear?
Oh, so
It's
you
a-
forgot G, sir.
I'm sorry. Is it
G.
0?
G.
Okay, that's okay. So G in degree by default, it's 1 is there. After this one is visited, it will become 0. Is it right?
Yes, sir.
This is visited so that it will become 0. So we can say that in the fourth term, uh, uh, can I finish these courses? Yes, I can finish up these 4 courses. In the fourth term, I can say that it's a green color. Clear?
Yes, sir.
So after that, these things you can finish up. So once this is done, then only you can finish up this one. Once J is done, then only you can do this one. So that this in degree still it's there. So that, but this one is can be done. So this can be done alone in the fifth term. Is it right?
Yes.
After doing this one only, this edge is removed. In the sixth term, I can do the last course. So basically, it requires that the longest path here is 6. The longest path is 6. What exactly is 6 number of years or 6 terms it requires to complete all of these courses in this one. So the similar lines, they want to find out it. Here also same in degree was taken, but longest path they want to compute it. So when they want to compute the longest path, yeah, here it is. Here there is in degrees, okay. Yeah, here it is. Please look at here. The longest path value of this one is the longest path of adjacency vertex or adjacency vertex plus 1. Either current one is the longest path, one is the longest one, or current one, sorry, current adjacent vertex is the longest one is there. That is considered, or current vertex plus 1, because current vertex means currently whatever visited one. Out of this one, maximum is taken, that maximum is considered, that is written. So here 0th one can be finished in 0th term only. First also you can finish the first term, but in the second term, what you can say that 0th term, first term you can finish all of these. Second course, third course, fourth course you can finish in the first term. Of course, first term means it's a second term. In the third term, I can finish only 5. Is it right? Because based on that graph was given. In the third term, I can finish only the 6th, course number 6. In the fourth term, I can finish up this. So totally, the longest path from 0 to 4 is totally 5 terms are required to finish up this all of these courses. You know that is what a complete focus without breaking any term, completing as usual, as per the sequence. You can finish up within that 5 terms. Of course, 0 to 4 means it's a 5. So why this one is, this kind of problems we'll ask you, the topological sorting algorithm is same, but outside story we change it. If you can see that the OPP examination of earlier terms, they will give that a cake recipe, cake. They are making a cake. What are the sequence of ingredients they want to add to make a cake? So to mix that each of the ingredient, maybe they required that 1 minute of time. So how much of time to complete this entire cake? So such kind of question they'll ask you. Similar way, there is a construction of building is going on. Outside story changed. So to do this work, so totally how many number of days required to complete all of this construction? How many number of months are required? Such kind of outside story, they'll change it. But the concept is same. So in degree, every time we are trying to reduce it based on the earlier visited vertex, we try to remove that edge. So this is one of the application of DFS. Depth only it is going, but it's acyclic graph, and that too, it's a directed acyclic graph. It is not undirected; it's a directed acyclic. So that is maybe, as in the beginning session I said, from the week 4 the complex data structures are there. I strongly recommend you that kindly walk through this particular lecture in a fast forward manner. You can increase the speed and see that, or you can see that earlier term best sessions are there. Even myself or Atul, whichever you like it, you directly go to the point and understand it. And most important topic, because definitely this question, one of the programming question of OPP examination, you can expect from the week 4 and 5. There are 30 marks is there. That is the toughest question. One question from dynamic programming, one question from greedy method, one question from linked list, one question from log and complexity. There are 4 problems are given. I think OPP is 4 problems or not? Is it 4? I think it's 4. Am I right? Is it 4 problems or 3 problems? Hello. Please be active even it is running out
Sir,
of time.
4 problems.
Yeah, in the 4 problems, first problem is definitely stacks and queues and linked list. Easy problem, so he'll ask you. Second problem, they will ask you that log and complexity, definitely searching and sorting. Is it right? Hello.
Sir?
Second problem, definitely they'll ask you that log and complexities, like sorting or searching. Okay.
Sorting and what?
Sorting or searching. Any one of these.
Search. Okay.
Searching, binary search.
Oh, yes. Binary search.
Yeah. Third one is there. That is definitely they'll ask you that in the graph algorithms. Outside story, they'll change it. Like I said, one core story, building construction, quick story, no? Similar kind of story, they'll frame it. Clear? And fourth problem is there. They might ask you in dynamic programming. Is it right?
Okay, sir. Okay.
So okay. I strongly say first understand the concept, then focus on the code. Don't directly by heart the code. It is very difficult. You can't understand. Okay.
Okay, sir.
Yeah. So hope we got everything. Any clarification, please let me know. And don't panic. Like it is very huge or something like. But once you another time you walk through the same lecture, quickly you can recollect the things. But as soon as possible, you can recollect the things whatever we learned. Okay.
Okay, sir.
Okay. So can we close the session?
Thank you, sir. Thank you.
Okay. Thank you. Have a nice day. Okay.
Thank you, sir.
Thanks, sir.
Okay then.
Thank you, sir.